Hello, I'm Herbie Lee, Professor of Statistics at the University of California, Santa Cruz. Welcome to this course on Bayesian statistics. There are two main philosophies of probability and statistics, Bayesian and frequentist. Most existing classes focus on the frequentist approach. Here, we will learn the Bayesian approach and some of its benefits. In particular, the Bayesian approach is better for dealing with uncertainty, both in terms of being able to quantify uncertainty and also for being able to combine uncertainties in a coherent manner. The interpretations of intervals make much more sense in the Bayesian paradigm. This course is meant to be largely self-contained. Thus, it starts with a brief review of some key concepts of probability, Bayes' theorem, and distributions. We will then have a quick review of frequentist inference, and then start on Bayesian inference, with comparisons and connections between the two. In the third module, we will learn more about priors and posteriors for discrete distributions, the Bernoulli, Binomial, and Poisson distributions. Finally, in the fourth module, we will discuss continuous distributions, especially the normal or Gaussian distribution, and apply it to linear regression. In this course, you will learn the difference between Bayesian and frequentist inference, the key concepts of Bayesian inference, and how to perform Bayesian inference in simple cases. Some calculations can be done by hand, others will be done on the computer. You will have the choice of using R or Excel. You're expected to choose one of R or Excel, but you can do both if that interests you. Otherwise, you can pick from the available computer demonstrations, which are listed as lectures. You don't need to watch both the R and Excel lectures, just the ones for the software you have chosen. The format of this class is a little different from a conventional class. We'll have less in the video and more in the exercises, because learning by doing is more effective than just watching a video of mathematical concepts. These are what would be homework assignments in an in-person course, but there isn't a label in Coursera for homework, so they are labeled as quizzes. But do think of them as homework assignments. We've tried to include a lot of additional explanation in the feedback, both for correct and incorrect responses. So you may need to try these homework assignments several times to get a passing grade, and the feedback is provided to assist you in learning the material. Items labeled background material should be read before watching the video lecture. Items labeled supplementary material follow the lecture and are more optional. One note on video resolution. We recommend that you watch at the highest resolution. You can see this from the settings, the gear icon in the lower right. Under video quality, choose high. You may need to watch a video more than once. If you're confused after the first watching, check the background and supplemental materials again, and then try watching the video again. You may even attempt some of the exercises, and then go back and watch the video. Learning is an iterative process, and so trying to work the exercises may provide context that helps make the video more understandable. In terms of prerequisites and expectations, I expect that you've taken an introductory statistics course and a calculus course. In both cases that you've seen the concepts before, but don't necessarily remember everything. I'll give refreshers for the statistical concepts, such as probability, the central limit theorem, confidence intervals, and regression, but I won't be providing a complete introduction. Similarly, I expect that you understand the concept of an integral and a derivative, and I will be using them as calculations, but none of the mandatory exercises will require you to integrate or differentiate, although some may require finding a simple area under curve, like finding the area of a rectangle. A few of the honors exercises will require calculus for those people who do remember how to integrate and differentiate. So my basic expectation is that you've taken calculus in an introductory statistics course at some point in your life, but it may be a long time ago and you've forgotten all the details. That's fine. I just need you to have seen it before so that when I use some of these, that will trigger some memories about the concepts and the bigger picture, so that the exact calculations aren't totally foreign for you. Statistics is the study of uncertainty. How do we measure it? And how do we make good decisions in the presence of it? One of the ways to deal with uncertainty in a more quantified way is to think about probabilities. Let's think about some examples of probabilities. Suppose we're rolling a fair six-sided die, and we want to ask, what's the probability that the die shows a 4? We could ask other questions. For example, is this a fair die? Does it make sense to ask, what is the probability that the die is fair? We could ask questions such as, what's the probability that it rains tomorrow? If we're dealing with the internet, we may have a router that's passing through information, and we can ask, what's the probability that it drops a packet? We might be comparing routers from two different companies, and we can ask, what's the probability that a router from one company is more reliable than a router from another company? We can ask more existential questions, such as, what's the probability that the universe goes on expanding forever? There are three different frameworks under which we can define probabilities. We'll talk about all of them briefly here. The first one is a classical framework. The second is a frequentist framework. And the third one is a Bayesian framework. Under the classical framework, outcomes that are equally likely have equal probabilities. So in the case of rolling a fair die, there are 6 possible outcomes. They're all equally likely. So the probability of rolling a 4 on a fair 6-sided die is just 1 in 6. We could ask a related question, which is, what is the probability of getting a sum of 4 on a pair of rolls? If we roll 2 dice, 2 fair 6-sided dice, then what's the probability that their sum shows a 4? Well, if we think about this, how many equally likely outcomes are possible on a pair of dice? There are 6 equally likely outcomes on the first die. There are 6 equally likely outcomes on the second die. So there are a total of 6 times 6, or 36 possible equally likely outcomes on the pair. Of those outcomes, how many will have a sum of 4? We could roll a 1 on the first die and a 3 on the second, a 2 on the first and a 2 on the second, or a 3 on the first and a 1 on the second. So there are a total of 3 possible outcomes out of 36 equally likely outcomes, and so that's a probability of 1 in 12. This classical approach works really well when we have equally likely outcomes, or a way to define equally likely outcomes, but it's very difficult to apply in any of these other cases. We can then move on to a frequentist definition. Frequentist definition requires us to have a hypothetical sequence, infinite sequence of events, and then we look at the relative frequency in that hypothetical infinite sequence. In the case of rolling a die, a fair 6-sided die, we can think about rolling the die an infinite number of times. This is pretty straightforward. If it's a fair die, if we roll an infinite number of times, then 1/6 of the time we'll get a 4 showing up, and so we can continue to define the probability of rolling a 4 on a fair 6-sided die as 1 in 6. This also applies to situations such as internet traffic going through a router. If we lose 1 in 10,000 packets, then we can define the probability as 1 in 10,000. This approach works great when we can define a hypothetical infinite sequence. But then we can ask other questions, and they become more complicated under this approach. For example, what is the probability that it rains tomorrow? In this case, we need to think about a hypothetical infinite sequence of tomorrow and see what fraction of these infinite possible tomorrows have rain, which is a bit strange to think about. Or in the case of asking, is this a fair die? Well, if we have a particular physical die, and we're asking, is it a fair die, then we can roll it a lot of times, but that's not going to change whether or not it's a fair die. And so either it is fair or it isn't fair. All these rolls are not going to change that. And so under the frequentist paradigm, this probability is either 0 or 1. It's 0 if it's not a fair die, and it's 1 if it is a fair die. This is not exactly an intuitive answer. In the case of the universe expanding forever, we can ask, if this is a deterministic universe and the same thing happens, then again, the answer is going to be either 0 or 1, because every time we play forward the expansion of the universe, either it will expand forever or it won't. On the other hand, we might subscribe to something like a multiverse theory, where there are an infinite number of parallel universes that can exist. In that case, we can consider this infinite collection and ask what fraction of this infinite collection have universes that expand forever. Depending upon what we know about the universe, we might get different answers. The frequentist approach tries to be objective in how it defines probabilities, but as you can see, it can run into some deep philosophical issues. Sometimes the objectivity is just illusory. Sometimes we also get interpretations that are not particularly intuitive. Another way to define probabilities is under the Bayesian perspective. The Bayesian perspective is one of personal perspective. Your probability represents your own perspective. It's your measure of uncertainty, and it takes into account what you know about a particular problem. But in this case, it's your personal one, and so what you see may be different than what somebody else believes. For example, we want to ask, is this a fair die? If you have different information than somebody else, then your probability the die is fair may be different than that person's probability. It's inherently a subjective approach to probability, but it can work well in a mathematically rigorous foundation, and it leads to much more intuitive results in many cases than the frequentist approach. We can quantify probabilities by thinking about what is a fair bet. So for example, we want to ask what's the probability it rains tomorrow? And then we can ask about a bet that you might be willing to take if you think it's fair. Suppose you'd be willing to take the bet that if it rains tomorrow, you win $4. If it doesn't rain tomorrow, you lose $1, or whatever your local currency is. We can think of this as odds of 4 to 1. If you think that that's a fair bet, you should be willing to take it in either direction, which would also mean if it rains, you lose $4, and if no rain, you win $1. If you think these are both fair, then you're defining a probability of rain as 1 over 1 plus 4, which equals 1 in 5. We can see this is fair by looking at your expected return. Under the first bet, your expected return is you win 4 with probability 1 in 5, and you lose 1 with probability 4 in 5, and you can see that that's a fair bet of 0. In the second case, you win 1 with probability 4 in 5, and you lose 4 with probability 1 in 5, and that also is 0. So it balances out. It only balances out if your probabilities match. So you can use this betting framework to think about what is your personal probability based on what bets you'd be willing to take. In most cases, it's fairly easy to bracket it. You'd take a bet that was 1,000 to 1 in favor, but you wouldn't take a bet that was 1,000 to 1 against. And so your personal probability is somewhere in between. Finally, I want to mention the concept of coherence. Probabilities must follow all the standard rules of probability, those that were defined in the supplementary material for this lecture. If you don't follow all of the rules for probability, then you can be incoherent, which leads to a case where someone can construct a series of bets where you're guaranteed to lose money. This is referred to as Dutch book. If you do follow all the rules, and you follow the framework of Bayesian statistics, then you can be guaranteed to be coherent. In this segment, I will discuss conditional probability and Bayes' theorem. Bayes' theorem is the theoretical underpinning of most of what we do within the Bayesian statistical framework. Conditional probability is when we're trying to consider two events that are related to each other. So we can ask, what is the probability of event A given that we know event B happened? This is defined as the probability that both events A and B happen divided by the probability that event B happens. For example, consider a class of 30 students. Suppose within this class there are 9 female students. Suppose also we have 12 computer science majors, and of which 4 are female. So then we can ask questions about probabilities of this segment of population. We can say the probability that someone is female is 9 in 30, or 3 in 10. The probability someone is a computer science major is 12 over 30, or 2 in 5. The probability that someone is both female and a computer science major, we have the 4 out of 30. So now we can ask conditional probability questions. What's the probability that someone is female given they're a computer science major? So if we think about the definition, we can work with that. This is the probability that someone is female and they're a computer science major divided by the probability they're a computer science major. Probability that someone is female and computer science is right up here. This is 2 out of 15. And the probability they're a computer science major is 2 in 5. We can simplify this down to get that this probability is 1 in 3. We can also think about that in the original framework here. Of the 12 computer science majors, what fraction are female? That's exactly what this probability is saying. The probability that they're female given their computer science. And so there we could just look at the 4 over 12. That would give us the same answer of 1/3. That's an intuitive way to think about a conditional probability, is that we're looking at a subsegment of the original population and asking a probability question within that segment. We can also look in the other direction. Suppose we want to know what's the probability someone's female given they're not a computer science major, or I might denote that as CS complement. In this case, we can say it's the probability female and not computer science over the probability of not computer science. And this is 5 in 30 over 18 in 30, or 5 over 18. There's a concept of independence, which is when one event doesn't depend on the other. When two events are independent, we have that the probability of A given B is equal to just the probability of A. It doesn't matter whether or not B occurred. When this is true, we also get that the probability of A and B happening is just the probability of A times the probability of B. This is a useful equality that we'll use throughout this course. In this case, we can see that the probability of being female, given they're a computer scientist, is not equal to the marginal probability that they're female. And so being female and being computer science are not independent. Bayes' theorem is used to reverse the direction of conditioning. Suppose we want to ask, what's the probability of A given B, but we know it in terms of probabilities of B given A. So we can write the probability of A given B as the probability of B given A times the probability of A divided by the probability of B given A times the probability of A plus the probability of B given not A times the probability of not A. This does work out back to be the same as the probability of A and B over the probability of B. So to work this out in the context of the example of the computer science and females in the class, we can say the probability that someone's a computer scientist given they're female is the probability they're female given they're a computer scientist times the probability they're a computer scientist divided by the probability they're female given their computer science times the probability of computer science, same thing as there, plus the probability they're female given they're not a computer scientist times the probability they're not a computer scientist. Plugging in the numbers, we get 1/3 times 2/5 over 1/3 times 2/5 plus 5/18 times 3/5. Working this all out, this ends up as 4/9. We can compare this to the direct answer. Probably computer science given female, if we were to compute this as probability of computer science and female divided by the probability of female, that one would have worked out to be 4/30 over 9/30, which gives us the same 4/9. In this case, it's straightforward to get the answer either way. But here we're moving from a direct definition. Here, it's where we have it in terms of one direction of conditioning, and we flip it to the other direction of conditioning. This is particularly useful in a lot of problems where it's posed in that direction. Another example was an early test for HIV antibodies known as the Elisa Test. In that case, the probability that someone would test positive, given that they had the HIV virus, was 0.977. The probability that they test negative, given they don't have the virus, was 0.926. So this is a pretty accurate test. Over 90% of the time, it'll give you an accurate result. Today's tests are much more accurate, but in the early days, this was still pretty good. At that point, a study found that among North Americans, the probability that a North American would have HIV was about 0.0026. So then we could ask, if we randomly selected someone from North America and we tested them and they tested positive for HIV, what's the probability that they actually have HIV given they've tested positive? In this case, we don't have all the information to compute it directly as easily, but we have the information in the reverse direction of conditioning. And so this is the perfect time to use Bayes' theorem. Probably they have HIV given they test positive is the probability they test positive given they have HIV times the probability they have HIV divided by probability they test positive given they have HIV times the probability they have HIV plus the probability they test positive given they don't have HIV times the probability they don't have HIV. And now we can fill these pieces in. Before we go any further, I ask you to stop and think briefly. This is over 90% accurate. What sort of number do you expect to get in this case? All right. Let's do the calculation. Probably they test positive given they have HIV is 0.977. The probability that they have HIV is 0.0026. We repeat the same thing in the bottom of the denominator. And then the second term, the probability they test positive given they don't have HIV, that's 1 minus this. And the probability they don't have HIV, if we now plug that into a calculator, we get this probability to be 0.033. The probability they have HIV is less than 4%, even though they've tested positive on a test that is nominally quite accurate. Is this surprising? It is for most people. Why is this so? It's because this is a rare disease, and this is actually a fairly common problem for rare diseases. The number of false positives greatly outnumbers the true positives because it's a rare disease. So even though the test is very accurate, we get more false positives than we get true positives. This obviously has important policy implications for things like mandatory testing. It makes much more sense to test in a subpopulation where the prevalence of HIV is higher, rather than in a general population where it's quite rare. To conclude, Bayes' theorem is an important part of our approach to Bayesian statistics. We can use it to update our information. We start with prior beliefs, we'll collect data, we'll then condition on the data to lead to our posterior beliefs. Bayes' theorem is the coherent way to do this updating. In this segment, we will review some basic probability distributions, both discrete and continuous. The first one is the Bernoulli distribution. It's used when we have two possible outcomes, such as flipping a coin, where it could be heads and tails, or the cases where we have a success or a failure. We'll denote this as saying a random variable x follows a Bernoulli distribution with probability p, where p is the probability of success, or the probability of heads. The little squiggle refers to is distributed as, saying it follows this distribution. In this case, the probability of a success, or heads, we'll say is p, and we'll denote that sometimes as x equals 1, and a failure, or tails, x equals 0, as probability 1 minus p. We can write this as a function for all the different possible outcomes and say, what's the probability that the random variable x takes a value little x given a specific value of p? So the notation here is that the capital letters refer to the random variable, the lowercase letters refer to a possible value it might take. And then over here we have a probability specified for it. Later, when these probabilities are unknown, we'll represent that with a Greek letter rather than a Roman letter. We may write this in shorthand as just the f of little x given p, and dropping the big X from the notation. In the case of a Bernoulli, mathematically this works out to be p to the x, 1 minus p to the 1 minus x, for the case that x's are either 0 or 1. One way to write this is with an indicator function, that x is either 0 or 1. This indicator function we could write as a function of x, and it's a step function, or sometimes referred to as a Heaviside function. It takes value 1 when its argument is true, and it takes value 0 when its argument is false. This will be really useful notation for us in the rest of this course. The indicator function takes precedence in the order of operations, so we always evaluate it first. This is a way we can avoid doing things such as taking the log or the square root of a negative number. In basic textbooks, this is referred to as the probability mass function. It gives the probability of different outcomes of the random variable. In some textbooks, they make a strong distinction between discrete variables, where these are probably mass functions, and continuous variables, where these are probably density functions. Turns out if you get far enough along in math and you get up to the measure theory level, you can view everything as a density. And so I'm going to refer to this as a density function in a measure theoretic sense. One more concept is that of an expected value. This is the theoretical average or theoretical mean. We write it with a capital E, and the expected value of x is we sum over all possible outcomes, little x. We sum up x times the probability the random variable takes that value little x. In this case, it's really simple. One possible outcome is 1, and it takes that with probability p. Another possible outcome is 0, and it takes that with probability 1 minus p. So the expected value for Bernoulli is just the probability p. Similarly, we can talk about the variance, which is the square of the standard deviation. For Bernoulli, the variance works out to be p times 1 minus p. The generalization of the Bernoulli, when we have n repeated trials, is a binomial. Binomial is just the sum of n independent Bernoullis. We can say x follows a binomial distribution with parameters n and p. In this case, the probability function, probably that x takes some value little x given p, is n choose x times p to the x times 1 minus p to the n minus x. N choose x is the combinatoric term, n factorial over x factorial times n minus x factorial. And this is all for x taking values 1, 0, 1, up to n. The expected value for a binomial is n times p, And the variance for a binomial is n times p times 1 minus p. Other distributions that we may encounter include the multinomial, a further generalization, and the Poisson distribution. As we move over to continuous random variables, the math gets a little bit more complicated and requires a little bit of calculus. We can define a continuous random variable based on its probability density function, or PDF for short. The PDF is sort of proportional to the probability that the random variable will take a particular value in a differential calculus sense, because it can take an infinite number of possible values. The key idea is that if you integrate the PDF over an interval, it gives you the probability that the random variable will be in that interval. As a specific example, let's consider a uniform distribution. X is uniformly distributed between 0 and 1, so it can take any value between 0 and 1, and they're all equally likely. In this case, we can write the density, f of x, as being 1 if x is in the interval 0, 1, and 0 otherwise. We could also represent this as an indicator function, and it's just the indicator function that x is between 0 and 1. We can then think about how we might plot this as a function of x. So as x goes from 0 to 1, what does this look like? Well, it's 1 in that region, and it's 0 otherwise. Very simple. The most simple probability density function we have. We can then ask questions about probabilities. What's the probability that x will be between 0 and 1/2? Well, in order to get this probability, we can just integrate the density function. So this is the integral from 0 to 1/2 of f of x dx, the integral from 0 to 1/2 of just dx, because it's 1 in that range. And so this is just 1/2. If we look at the picture, we could see the picture here. And it's the area there. We could ask a similar question. What's the probability x is between 0 and 1/2 inclusive versus not including the endpoints? Well, the integral doesn't really depend on the endpoints being in or not. You're going to get the same answer. So this is 1/2. From a calculus sense, we can also ask what's the probability that x is equal to 1/2. Well, if we integrate from 1/2 to 1/2, we're just going to get a 0. Because there are an infinite number of possible outcomes, the probability of taking any particular one is going to be 0. Some key rules for probability density functions. It is going to be always true that the integral from -infinity to infinity of f of x dx has to add up to 1. Be probability 1 that something happens. Also has to be true that densities are non-negative for all possible values of x. We can write the expected value for a continuous random variable as the integral of x times f of x dx. So this is analogous to the sum that we had for a discrete variable. In general, the expected value of some function of x, g of x, we can write as the integral of g of x, f of x, dx. If we take the expectation of some constant times our random variable x, that's just the constant times the expected value of x, we can pull the constant out. Similarly, if we're looking at the expectation of a sum of two random variables, that's the sum of the two expectations. Finally, if we have independence, If x is independent of y, that symbol means independent, then the expected value of x times y is just the product of the expected values. Some particular examples of continuous distributions are next. Let's start with the exponential distribution. We can write x follows an exponential distribution with the rate parameter lambda. So these are events that are occurring at a particular rate, and the exponential is the waiting time in between events. For example, you're waiting for a bus. The bus comes once every 10 minutes, and then the exponential is your waiting time. This is particularly true for events coming from a Poisson process. The density function for x given lambda is lambda times e to the minus lambda x. This is for non-negative values of x. The expected value is 1 over lambda, and the variance is 1 over lambda squared. So in the case of a bus that comes once every 10 minutes, the rate is 1/10. Another example is the uniform distribution. We saw this already in the case where it's a uniform on 0, 1, but it could be on a larger interval. In fact, the endpoints could be unknown. It could be uniform between endpoints theta 1 and theta 2. This case, we'll write its density, x given theta 1 and theta 2, as 1 over theta 2 minus theta 1 times the indicator function that x is between theta 1 and theta 2. Final example I want to mention right now is the normal distribution, also known as the Gaussian distribution. We say that x follows a normal distribution with mean mu and variance sigma squared. In this case, its density function is 1 over the square root of 2 pi sigma squared times e to the minus 1 over 2 sigma squared x minus mu squared. This has mean mu and variance sigma squared. In the supplemental material are some additional important distributions, such as the gamma distribution and the beta distribution. Next, let's do a brief review of the frequentist approach to inference, which will be useful for contrasting with the Bayesian approach. Under the frequentist paradigm, we view the data as a random sample from some larger, potentially hypothetical population. We can then make probability statements, i.e. long-run frequency statements, based on this larger population. As an example, let's suppose we flip a coin 100 times, and we get 44 heads and 56 tails. We can view these 100 flips as a random sample from a much larger, infinite hypothetical population of flips from this coin. In this case, we can say that each flip x sub I follows a Bernoulli distribution with some probability p. In this case, p may be unknown, but we're assuming it's fixed because we have a particular physical coin. We can ask what's our best estimate of the probability of getting a head, our estimate of p. We can also ask how confident are we in that estimate. We can start down the mathematical approach by applying the central limit theorem. Appealing the central limit theorem says that the sum of the 100 flips, sum of the x sub i's, will follow approximately a normal distribution with mean 100 times p and variance 100 times p times 1 minus p. Here I'm writing the squiggle with the dot above and below to mean approximately follows the distribution. By the central limit theorem, we have this distribution, and so by properties of normals, 95% of the time, we'll get a result within 1.96 standard deviations of the mean. Thus, we can say 95% of the time, we expect to observe between 100p minus 1.96 times the square root of 100p 1 minus p, and 100p plus 1.96 times the square root of 100 times p times 1 minus p. In this case, we've observed 44 heads. So then we can estimate the probability of getting a head and write that p hat, our estimate of p, as 44 over 100. We can then go back and plug this value into our theoretical quantity. This is what's referred to as a confidence interval in this case. Confidence interval we may abbreviate CI. The confidence interval is then going to be 44 plus or minus 1.96 times the square root of 44 times 0.56. Or in this case, this is 44 plus or minus 9.7, or the interval that goes from 34.3 to 53.7. So we can say that we're 95% confident that p is in the interval 0.343 to 0.537. We're 95% confident that the true probability of getting ahead is in this interval. So if we want to ask the question, do we think this is a fair coin, then it is reasonable that this is a fair coin because 1/2 is in this interval. But we can also step back and say, what does this interval really mean? What does it mean when I say we're 95% confident? Under the frequentist paradigm, what this means is we have to think back to our infinite hypothetical sequence of events. So if we were to repeat this trial an infinite number of times, or an arbitrary large number of times, each time we create a confidence interval in this way based on the data we observe, then on average, 95% of the intervals we make will contain the true value of p. This makes sense as a long-run frequency explanation. On the other hand, we might want to know something about this particular interval. Does this interval contain the true p? What's the probability that this interval contains the true p? Well, we don't know for this particular interval, but under the frequentist paradigm, where we're assuming that there is a fixed right answer for p, either p is in that interval or it's not in that interval. And so technically, from a frequentist perspective, the probability that p is in this interval is either 0 or 1. This is not a particularly satisfying explanation. On the other hand, when we get to the Bayesian approach, we will be able to compute an interval and actually say the probability that p is in this interval is 95%, based on a random interpretation of an unknown parameter. Next, let's do a brief review of the frequentist approach to inference, which will be useful for contrasting with the Bayesian approach. Under the frequentist paradigm, we view the data as a random sample from some larger, potentially hypothetical population. We can then make probability statements, i.e. long-run frequency statements, based on this larger population. As an example, let's suppose we flip a coin 100 times, and we get 44 heads and 56 tails. We can view these 100 flips as a random sample from a much larger, infinite hypothetical population of flips from this coin. In this case, we can say that each flip x sub I follows a Bernoulli distribution with some probability p. In this case, p may be unknown, but we're assuming it's fixed because we have a particular physical coin. We can ask what's our best estimate of the probability of getting ahead, our estimate of p. We can also ask how confident are we in that estimate. We can start down the mathematical approach by applying the central limit theorem. Appealing the central limit theorem says that the sum of the 100 flips, sum of the x sub i's, will follow approximately a normal distribution with mean 100 times p and variance 100 times p times 1 minus p. Here I'm writing the squiggle with the dot above and below to mean approximately follows the distribution. By the central limit theorem, we have this distribution, and so by properties of normals, 95% of the time, we'll get a result within 1.96 standard deviations of the mean. Thus, we can say 95% of the time, we expect to observe between 100p minus 1.96 times the square root of 100p 1 minus p, and 100p plus 1.96 times the square root of 100 times p times 1 minus p. In this case, we've observed 44 heads. So then we can estimate the probability of getting a head and write that p hat, our estimate of p, as 44 over 100. We can then go back and plug this value into our theoretical quantity. This is what's referred to as a confidence interval in this case. Confidence interval we may abbreviate CI. The confidence interval is then going to be 44 plus or minus 1.96 times the square root of 44 times 0.56. Or in this case, this is 44 plus or minus 9.7, or the interval that goes from 34.3 to 53.7. So we can say that we're 95% confident that p is in the interval 0.343 to 0.537. We're 95% confident that the true probability of getting a head is in this interval. So if we want to ask the question, do we think this is a fair coin, then it is reasonable that this is a fair coin because 1/2 is in this interval. But we can also step back and say, what does this interval really mean? What does it mean when I say we're 95% confident? Under the frequentist paradigm, what this means is we have to think back to our infinite hypothetical sequence of events. So if we were to repeat this trial an infinite number of times, or an arbitrary large number of times, each time we create a confidence interval in this way based on the data we observe, then on average, 95% of the intervals we make will contain the true value of p. This makes sense as a long-run frequency explanation. On the other hand, we might want to know something about this particular interval. Does this interval contain the true p? What's the probability that this interval contains the true p? Well, we don't know for this particular interval, but under the frequentist paradigm, where we're assuming that there is a fixed right answer for p, either p is in that interval or it's not in that interval. And so technically, from a frequentist perspective, the probability that p is in this interval is either 0 or 1. This is not a particularly satisfying explanation. On the other hand, when we get to the Bayesian approach, we will be able to compute an interval and actually say the probability that p is in this interval is 95%, based on a random interpretation of an unknown parameter. Let's do another example. Consider a hospital where 400 patients are admitted over a month for heart attacks, and a month later, 72 of them have died, and 328 of them have survived. We can ask, what's our estimate of the mortality rate? Under the frequentist paradigm, we must first establish our reference population. What do we think our reference population is here? One possibility is we could think about heart attack patients in the region. Another is we could think about heart attack patients that are admitted to this hospital, but over a longer period of time. Both of these might be reasonable attempts, but in this case, our actual data are not a random sample from either of those populations. We could sort of pretend they are and move on, or we could also try to think harder about what a random sample situation might be. One would be is we could think about all people in the region who might possibly have a heart attack and might possibly get admitted to this hospital. It's a bit of an odd hypothetical situation, and so there are some philosophical issues with the setup of this whole problem within the frequentist paradigm. In any case, let's forge forward and think about how we might do some estimation. We can say each patient comes from a Bernoulli distribution with unknown parameter theta. I'm now going to use the Greek letter theta because this is an unknown we're really trying to estimate. So the probability that yi equals 1 is equal to theta for all the individuals admitted. In this case, we're going to say that a success is mortality. The probability density function for the entire set of data we can write in vector form. Probably all of the y's take some value little y, given a value of theta. So this is the probability y1 takes some value little y1, y2 takes some value little y2, 0 or 1, and so on up to yn. Because we're viewing each of these as independent, then this is just the probability of each of these individual ones. So we can write this in product notation. And applying what we know about a Bernoulli, this then works out to be theta to the y sub I times 1 minus theta to the 1 minus y sub I. This is the probability of observing the actual data that we collected conditioned on a value of the parameter theta. We can now think about this expression as a function of theta. This is the concept of a likelihood. The likelihood function is this density function thought of as a function of theta. So we can write this L of theta given y it looks like the same function, but up here this is a function of y given theta, and now we're thinking of it as a function of theta given y. This is not a probability distribution anymore, but it is still a function for theta. One way to estimate theta is that we choose the theta that gives us the largest value of the likelihood. It makes the data the most likely to occur for the particular data we observed. This is referred to as the maximum likelihood estimate, or MLE, maximum likelihood estimate. It's the theta that maximizes the likelihood. In practice, it's usually easier to maximize the natural logarithm of the likelihood, referred to as the log likelihood. At this point, we usually drop the conditional notation on y as well. Since the logarithm is a monotone function, if we maximize the logarithm of the function, we also maximize the original function. In this case, we're dealing with data that are independent and identically distributed. Sometimes we write that then as y sub I, independent and identically distributed, IID, Bernoulli's theta. With independent identically distributed data, the likelihood is a product because they're independent. And therefore, when we take the log of a product, we get a sum, and sums are much easier to work with. So in this case, the log likelihood is the log of the product of theta to the y sub I, 1 minus theta to the 1 minus y sub I. The log of a product is the sum of the logs. And when we take the log of the inside, the log of theta to the y sub I, we'll get simplification there as well. So that becomes y sub I times the log of theta plus 1 minus y sub I times the log of 1 minus theta. Now we can pull the thetas out because they don't change with I as we take the sum. And so this turns into the sum of the y sub i's times the log of theta plus the sum of 1 minus y sub I times the log of 1 minus theta. How do we find the theta that maximizes this function? If you recall from calculus, we can maximize a function by taking the derivative and setting it equal to 0. So we take the derivative of the log likelihood, which I'm going to denote L prime of theta. Taking the derivative here, the derivative of log of theta is 1 over theta. And then we subtract from that 1 over 1 minus theta times the sum of the 1 minus y sub i's. We then set this equal to 0 and solve for theta. This gives us the sum of the y sub i's over theta hat equals the sum of 1 minus y sub I over 1 minus theta hat, where I'm plugging in now the theta hat that will make this set equal to 0. This results in a theta hat value of 1 over n times the sum of the y sub i's. This is in fact the same p hat that we got earlier from the other approach, or in this case 72 over 400 gives us a 0.18. And so that's our maximum likelihood estimate of the probability. You can see we got the same estimate as before, and this is one of the reasons that we use the obvious estimator. Maximum likelihood estimators have many desirable mathematical properties. They're unbiased, they're consistent, and they're invariant. In this case, we can also use the central limit theorem to give us an approximate confidence interval. From the central limit theorem, we get a confidence interval of theta hat plus or minus 1.96 times the square root of theta hat times 1 minus theta hat over n. In general, under certain regularity conditions, we can say that the MLE is approximately normally distributed with mean at the true value of theta and variance 1 over the Fisher information evaluated at theta hat. We'll return to the Fisher information later. The Fisher information is a measure of how much information about theta is in each data point. It's a function of theta. For a Bernoulli random variable, the Fisher information turns out to be 1 over theta times 1 minus theta. So the information is larger when theta is near 0 or near 1, and it's the smallest when theta is near 1/2. This makes sense because if you're flipping a coin and you're getting a mix of heads and tails, that tells you a little bit less than if you're getting nearly all heads or nearly all tails. That's a lot more informative about the value of theta. We'll return to the calculation of the information later in this course. Some more examples of maximum likelihood estimators. The exponential distribution. Suppose that we have samples from an exponential distribution with parameter lambda. Recall that the density is the product of lambda e to the minus lambda x sub I. Working on this product, we can actually collapse it so that this is lambda to the n times e to the minus lambda times the sum of the x sub i's. Thus the likelihood function as a function of lambda given x is lambda to the n, e to the minus lambda, sum of the x sub i's. If we take the log of this, we get the log likelihood, which is n log lambda minus lambda times the sum of the x sub i's. If we take the first derivative of this, we get n over lambda minus the sum of the x sub i's. We set that equal to 0. This gives us a maximum likelihood estimate lambda hat of n over the sum of the x sub i's, or 1 over the average. This makes sense, because the mean for an exponential distribution is 1 over lambda. And so if we take 1 over the sample average, we get a maximum likelihood estimate for lambda. Another example would be a uniform distribution. Suppose the x sub i's, or IID, from a uniform distribution where we know it starts at 0, but the upper endpoint theta is unknown. In this case, our density function is the product from I goes from 1 to n of 1 over theta, the density, times an indicator function that all of the observations are between 0 and theta. The likelihood then we can rewrite as L of theta given x. The product of these 1 over thetas is just theta to the minus n. Combining all the indicator functions, for this to be a 1, each of these has to be true. These are each going to be true if all of the observations are bigger than 0, as in the minimum of the x's is bigger than or equal to 0, and then the maximum of the x's is less than or equal to theta. In this particular case, we don't have a need for a logarithm. It's not actually going to help us. This is one of the few exceptions where the logarithm is not so helpful. So we'll look directly at the derivative of the likelihood itself. Derivative of theta to the minus n is minus n to the theta to the n minus 1, or minus n plus 1. And then this indicator function hangs around. They don't go away when you take derivatives, they just hang around. So now we can ask, can we set this equal to 0 and solve for theta? Well, it turns out this is not equal to 0 for any theta positive value. We need theta to be strictly larger than 0. This will never be 0 in that interval. However, we can also note that for theta positive, this will always be negative. If the derivative is negative, that says this is a decreasing function. So this function will be maximized when we pick theta as small as possible. What's the smallest possible value of theta we can pick? Well, we need in particular for theta to be larger than all of the x sub i's. And so the maximum likelihood estimate is the maximum of the x sub i's. We find the largest value of our data, and that's the smallest possible value theta could be, and that's our maximum likelihood estimate. R is an open source statistical software package. It can be freely downloaded at rproject.org. There are other Coursera courses that provide detailed lessons on using R. Here I will just provide a short introduction to try to get you using R for the tasks needed in this course. First, launch R. R will do basic arithmetic. You can just type in an expression and hit enter. For example, 1 plus 2 times 3. As you can see, R knows the correct order of operations. R is an object-oriented environment, meaning that almost everything it does revolves around objects. Objects have names, and you can assign values to objects. For example, assigning a number. We can have an object x and assign the value 6 to it by typing in x equals 6. If we want to see the value, we can then enter the name of the object, and R will display the value. We can also use descriptive names. For example, total revenue, and assign that a value of 18.4. We can copy an object by assigning it to another name. If I have expenses, and that has a value of 6, but I already have 6 in x, I can just say expenses equals x. You can also assign the result of an operation to an object. For example, net profit would be total revenue minus expenses. We type in just the name of the object and it will give us the value in it. And you can see here that it's done the subtraction and saved to the result. You have some flexibility with names, but you can't use certain characters such as spaces in a name. R also has functions. To run a function, you type its name followed by parentheses with any arguments in the parentheses. For example, the C function will store a column of data, or it will concatenate data. We might want to assign to a variable z the set of data that goes 2, 3, 4, 5, and 6. You can see this data set is now stored in the object z. It stores it as a vector. We can then use functions to get more information or do analysis on these objects. We can ask, what's the mean or average of the values in z? We can ask, what's the variance of z? Or what's the standard deviation of z, which is the square root of the variance? We can use a function to create a sequence. The seq function creates a sequence, and we tell it what the starting point is, the from value, what the ending point is, the to value, and what increment we want to use, the by variable. This gives us a sequence that goes from point 1 to point 9, going in increments of point 1. Here we specified 3 arguments, and we've given them all by name. If we don't name the arguments, we can just specify numbers, and R will fill them in order. Any arguments we don't specify will get the default value, assuming they're at the end of the list. So for example, if we say sequence from 1 to 10, it's filling them in order. The first number we give is the from, the second number is the to, and then we haven't specified a by, and it will use the default, which in this case is by once at a time. And so this will give us a sequence that goes from 1 to 10. Let's take a brief look at one of the built-in data sets in R. This is the trees data set. This is a set of trees, and it gives us the diameter, the height, and the volume of the tree. We can learn some more by using the help function. This opens up a new window and gives us information about the data set, including references and some examples of analysis. It gives us some more definition showing that, indeed, this is a diameter, a height, and a volume. As you see here, there are labels for each of these columns. They're named. We can access these names in R by using the attach command. This says to look in the trees object for other additional names. We can ask what are the names by using the names command. And these are the same ones that we see when we look at the data set itself. We can then use these names to directly access these variables. For example, we want to make a histogram of the girth or diameter of these trees. When we say hist, it's a histogram function, and it automatically pops up a new window for us. From the histogram, we can see that most of the trees have diameters between 8 and 18 inches, with one larger tree. We can also make scatter plots, putting the girth on the x-axis and the height on the y-axis to see how height relates to diameter. As you can see here, in general, the wider the tree, the taller the tree. There's a function in R called pairs, which allows us to make all possible pairwise scatter plots for the data set. So if we say pairs of trees, we have each of the 3 variables plotted against each of the other ones. So for example, in this box here, we have girth on the x-axis and height on the y-axis. And this is exactly the plot that we just had previously. In the lower left here, we have girth on the x-axis and volume on the y-axis. And we can see there's a very strong relationship between total volume of timber in the tree and how wide the tree is. Similarly, there's a strong relationship between the height of the tree and the volume of the tree. In the upper corner, we have the mirror images of these plots with the variables on the opposite axes. And so this plot here in the upper right has volume on the x-axis and girth on the y-axis. Finally, we can get numerical summaries using the summary command. For each of the variables, this will give us the mean, the median, the range, and the quantiles. In the video lecture, we talked about a hospital with 400 heart attack patients, of whom 72 die within 30 days and 328 are still alive. Let's plot the likelihood function for this example. We could use either a binomial likelihood or a Bernoulli likelihood. These are actually the same other than a constant term in the front, the combinatoric term for the binomial, that does not depend on theta. So we'll be getting the same answers, it's just a little rescaling on the vertical axis. It's much simpler to stick with the Bernoulli likelihood that doesn't have the combinatoric terms. The likelihood is a function of the mortality rate theta. So we'll create a function in R. We can use the function command and store our function in an object. We can call this object likelihood. Use the function command, and we specify what arguments this function will have. We'll need total sample size n, the number of deaths y, and the value of the parameter theta. We specify the function inside of curly braces. In this case, all we needed to do is return a computed value. So we'll use the return function to return that value, and here we just put in the likelihood formula, which in this case is theta to the y times 1 minus theta to the n minus y. To plot the likelihood, we'll create a sequence of points with mortality rates between 0 and 1, and then plot the likelihood values over that sequence. So I'll define a sequence of values for theta using the sequence command. Here we go from 0.01 to 0.99 in increments of 0.01. We can now plot this. We're going to call the likelihood function over this sequence using n equals 400, y equals 72, and our vector theta. This pops up a plot. And if we look carefully, we can see that the likelihood is maximized at the value 72 over 400, or 0.18. This might be a little bit difficult to see in the plot, and so one thing that can help is we can add a vertical line using the AB line command and say vertical line at 0.18. Adding that in makes it really clear that this likelihood is maximized at 72 over 400. We can also do the same with the log likelihood, which in many cases is easier and more stable numerically to compute. We can define a function for the log likelihood, say log like, which again is a function of n, y, and theta. Here, we'll return the value from the log likelihood, which is y times the log of theta plus n minus y times the log of 1 minus theta. Now, we can plot the sequence against the log likelihood of that sequence. It's a smoother function, a little bit more difficult to see where the maximum is. Again, adding a vertical line helps us see the maximum at 0.18. Plotting this as a series of points doesn't give us necessarily the best picture. We could actually do this as a line plot instead. In R, we can use the up arrow to go back to a previous command we've run. So if I hit up 3 times, I can get back to the function or to one of the plots. Here I can add another argument. The plot command has many, many possible optional arguments. One of them is the type of plot. If I say type equals double quotation lowercase l, that tells R to make a line plot. In the video lecture, we talked about a hospital with 400 heart attack patients, of whom 72 die within 30 days and 328 are still alive. Let's plot the likelihood function for this example. The likelihood is a function of the mortality rate theta. We could use either a binomial likelihood or a Bernoulli likelihood. They are the same other than a constant term in the front the combinatoric term for the binomial that does not depend on theta. So we'll get the same answer either way, and it's easier to use the Bernoulli likelihood. We can plot this in Excel. We'll need to create a column of theta values and a column of likelihood values. For the theta values, we'll want it to go from 0.01 up to 0.99 in increments of 0.01. We can create this column by using the fill command. Edit, fill, series. We want to put the series in a column. We'll grow linearly, have a step value of 0.01, and go all the way up to the value of 0.99. So now Excel has filled it in from 0.01 up to 0.99. For the likelihood, we'll create a function. So we start with the equal sign to create a function. And this is theta to the y times 1 minus theta to the n minus y. The value of theta we're going to plug in is the value in the adjacent column. We take this to the y power, in this case y is 72. We'll multiply this by 1 minus theta to the n minus y, where n is 400 and y is 72. We have this formula now defined for the first row. What we can do is we can copy this formula and then paste it in to all the remaining cells. Excel has now filled in the likelihood values for us and recomputed them for each of the possible theta values. In order to make a plot of this, we'll use a chart. So I'll highlight the column with the likelihood values. Go to Charts, choose a line chart, and do a basic line chart. If you look carefully, you may be able to see that the likelihood function is maximized at 0.18, or 72 over 400. This is the maximum likelihood estimate. We could also do the same with the log likelihood. This formula is going to be y times the log of theta plus n minus y times the log of 1 minus theta. So we can enter this as a formula in Excel with equals y is 72 times the log of the theta value from this column, this row, plus n minus y times the log of 1 minus the theta value. Again, we can copy that into the remaining cells. Paste. We highlight this column and create a line chart for the log likelihood. It's a little bit harder to see, but the log likelihood is also maximized at 0.18. Let's look at another simple example. This one just has two possible outcomes. This way we can compare both the frequentist and the Bayesian approaches to inference. Suppose your brother has a coin which you know to be loaded so that it comes up heads 70% of the time. He then comes to you with some coin, you're not sure which one, and he wants to make a bet with you, betting money that it's going to come up heads. You're not sure if it's the loaded coin or if it's just a fair one, so he gives you a chance to flip it 5 times and just check it out. You flip it 5 times and you get 2 heads and 3 tails, and now you have a decision point to make. Which coin do you think it is? And how sure are you about that? So in order to perform inference, we need to define a likelihood. In this case, we'll start by defining the unknown parameter theta, and this is either the coin is fair or it's a loaded coin. So our unknown parameter is which coin it is. Is it a fair coin or is it the loaded coin? Our data are going to be 5 flips of this coin. It's a binomial with 5 flips, and the question is, what's that probability? So we can write a likelihood, f of x given theta, as if it's the fair coin, this will be 5 choose x, 1/2 to the 5th. If it's the loaded coin, this will be 5 choose x, 0.7 to the x, 0.3 to the 5 minus x. We can rearrange this also to write it with indicator functions. Now in this case, we've observed x equals 2. What's our likelihood? We can write f of theta given x equals 2. In this case, I'm just going to switch back to using f instead of using a capital L for likelihood. On the frequentist paradigm, we're typically using capital L's. As we move over to the Bayesian paradigm, we're just going to use f's everywhere. It's really just a notational thing. We can now plug in x equals 2, and we get 0.3125 if theta equals fair, and 0.1323 if theta equals loaded. So we see that having observed 2 heads, the likelihood is higher for theta equals fair than for theta equals loaded. Thus we can say the maximum likelihood estimate, theta hat, is that this is a fair coin. That's our maximum likelihood estimate. Given the data, it is most likely that the coin is fair. That's a good point estimate, but then how do we answer the question, how sure are you? This is not a question that's easily answered in the frequentist paradigm. Another question is that we might like to know, what is the probability that theta equals fair, given we observed 2 heads? In the frequentist paradigm, the coin is a physical quantity. It's a fixed coin, and therefore it has a fixed probability of coming up heads. It either is the fair coin or it's not the loaded, or it's the loaded coin. In this case, the probability it's fair, given x equals 2, is just the probability that it's fair because it's a fixed coin. And this probability is either 0 or 1. This is not a particularly satisfying answer. As a result, let's take a look at how we'd solve this problem under Bayesian inference and see what type of answer we get there. Now let's take a look at the Bayesian approach. An advantage of the Bayesian approach is it allows you to easily incorporate prior information when you know something in advance of looking at the data. This is difficult to do under the frequentist paradigm. In this case, we're talking about your brother. You probably know him pretty well. Because you've been around him a bunch, and this isn't the first time he's come to you with a coin, you may have some information on this that you want to incorporate into the problem. So suppose you think that before you've looked at the coin, there's a 60% probability that this is the loaded coin. In this case, we put this into our prior. Our prior is that the probability the coin is loaded is 0.6. We can now update our prior with the data to get our posterior beliefs, and we do this using Bayes' theorem. F of theta given x is going to be f of x given theta times f of theta over all possibilities for theta of f of x given theta, f of theta. In this case, the only two possibilities for theta are that it's fair or loaded. So this likelihood is the same as what we saw before, but this time we'll be adding in the prior. 1/2 to the 5th times the prior probability that the coin is fair, plus 0.7 to the x, 0.3 to the 5 minus x, times the prior probability it's loaded, if we plug in our observed data x equals 2, this will work out to be 0.0125 theta equals fair, plus 0.0079 theta equals loaded, over 0.0125 plus 0.0079. Simplifying this, we get 0.612 theta equals fair, plus 0.388 theta equals loaded. As you can see in the calculation here, we have the likelihood times the prior in the numerator, and in the denominator, we have a normalizing constant, so that when we divide by this, we'll get answers that add up to 1. These numbers match exactly in this case because it's a very simple problem. But this is the concept that goes on. What's in the denominator here is always a normalizing constant, so that at the end of the day, we get probabilities. And so we can say at the end of the day here, the probability theta equals loaded, given x equals 2. So our posterior probability that this is the loaded coin works out to be 0.388. Isn't that a much more satisfying answer under the Bayesian approach, where we get a probability, and we can interpret this probability? We can say, what is the probability that we think this coin is loaded after we've observed some data? This is a much more intuitive answer than we get under the frequentist paradigm. We can also examine what would happen under different choices of prior. We did this calculation with a prior probability of 0.6 for the coin being loaded, but we might have a different idea. We want to use a different probability. We can use anything between 0 and 1. Or maybe somebody else is coming in with a different perspective, and they want to see what their answer is using a different prior. One possibility is that we could say the probability the coin is loaded in prior is 1/2. This might represent an attempt to say, we're not sure what's going on, it's equally likely that it's the loaded coin or the fair coin. Not that these are necessarily equally likely outcomes. Taking a prior probability of 1/2, we can put it through Bayesian machinery, and that will lead us to get a posterior probability, theta equals loaded, given we observe 2 data points. That works out to be 0.297. We might have a different idea. We might think, because this is our brother and we know him well, that the prior probability it's going to be the loaded coin is 0.9. He really likes to use the loaded coin. If this is the case, then when we go through the calculations, we'll get a posterior probability that this is a loaded coin of 0.792. In this case, the Bayesian approach is inherently subjective. It represents your own personal perspective. And this is an important part of the paradigm. If you have a different perspective, you will get different answers. And that's okay. It's all done in a mathematically rigorous framework, and it's all mathematically consistent and coherent. In the end, we get results that are interpretable. It makes sense. We want to ask, what is the probability the coin is loaded after we've looked at some data, incorporating our beliefs about our past experiences with our brother? This way, we get intuitive answers. We can say the probability it's loaded is 0.3, or the probability it's loaded is 0.8. Under the frequentist paradigm, we can't get a good answer for what is the probability the coin is loaded. The machinery just is not set up that way. It's not possible to get a good confidence interval. What would it even mean to have a confidence interval for is the coin loaded? The frequentist approach has a number of buried assumptions. We need to make a choice, which is inherently subjective, about what is our reference population. about what is our likelihood. These are assumptions that are inherently subjective, that are buried deeper into the frequentist paradigm. And so there's an attempt to pretend that everything is objective. Under the Bayesian paradigm, we're explicit that this is a subjective and personal approach, but we can also be explicit about what all of our assumptions are, and then see how our answers depend on our assumptions. Let's take a look at a more general case. Continuous version of Bayes' theorem is that f of theta given y is equal to f of y given theta times f of theta over f of y, or we can write that of f of y given theta times f of theta over the integral of f of y given theta times f of theta d theta. We can see that this is the likelihood times the prior divided by a normalizing constant. Likelihood times the prior, and then this is just a constant that will make sure that this integrates to 1, because we need this at the end of the day to be a proper probability density function. And it's clear that this will integrate to 1 because we're dividing by exactly what it is on top. In practice, sometimes this integral can be a pain to compute. And so we may work with looking at saying this is proportional to the likelihood times the prior. And if we can figure out what this looks like and just put the appropriate normalizing constant on at the end, we don't necessarily have to compute this integral. So for example, suppose we're looking at a coin and it has unknown probability theta of coming up heads. Suppose we express ignorance about the value of theta by assigning it a uniform distribution. So we can write f of theta is just the indicator function that theta is between 0 and 1. Now we flip the coin and we get one head. We want to say, having observed one flip of the coin, what's our posterior probability distribution for theta? So f of theta given y is this expression here. In practice, trying to compute this in more general form, we can do it, but it'll be a little bit more work. Let's go ahead and plug in f of theta given we've observed a head, given y equals 1. So this will be theta to the 1 minus theta to the 0, times the indicator function that theta is between 0 and 1, divided by the integral of all of this. D theta. So this simplifies on top to theta times the indicator function. In the bottom, this will be the integral now from 0 to 1 of theta d theta. The integral of theta d theta is going to be 1/2 theta squared. We evaluate that on 0, 1, and we just get 1/2. So this whole thing simplifies to 2 theta times the indicator function that theta is between 0 and 1. As a side note, we could do this whole thing in terms of proportionality. F of theta given y is proportional to f of y given theta times f of theta. And so we can say that's proportional to theta times the indicator function, that theta is between 0 and 1. And then we just need to normalize this so that it will integrate to 1. And as we saw earlier, then, taking the integral of this, the correct normalizing constant is that we just stick a 2 on this. So this is the same type of approach. We get to the same answer if we stick the normalizing constant on at the end, if we can recognize what this is at the end. In some cases later, this will turn out to be much easier to just use the proportionality approach rather than a full equality approach and trying to work out the integral. Let's take a look at plotting the prior and the posterior. So plotting the prior density for theta, it looks like this. It's uniform on 0, 1. The posterior density is a little bit different. We saw that is now 2 theta, and so that looks like this. So graphically, we can see that under the posterior, theta is much more likely to be close to 1 than to 0 because we saw one head. We can look at posterior and prior interval estimates. Under the prior, the probability that theta is between 0.025 and 0.975 is 0.95. It's a 95% prior probability interval. We can also say the probability theta is greater than 0.05 is 0.95. Graphically, we can think about that as thinking about integrating regions under the density. But because it's uniform, it's really simple to compute. We can then think about posterior interval estimates. Under the posterior density, we can ask, what's the probability that theta is between 0.025 and 0.975? In this case, we have a little integral to do. So we integrate from 0.025 to 0.975 the density of 2 theta d theta. The integral of 2 theta is going to be theta squared. And so this works out to be 0.975 squared minus 0.025 squared. And this happens to be 0.95. And so it turns out in this case to be the same as under the prior. You can look at the picture and think about just moving some of the pieces around. If you're chopping off both ends, we still end up with the same amount in the middle. However, if we ask the second question under the posterior, what's the probability theta is bigger than 0.05? This is now, when we run through the integral, 1 minus 0.05 squared. And this turns out to be 0.9975. There's very little chance now that theta is less than 0.05, having observed a head. This is a big change now from the prior to the posterior. Now these we're looking at sort of intervals we would get from the prior and saying what's their posterior probability. In other cases, we may want to ask, what is a posterior interval of interest? What's an interval that contains 95% of posterior probability in some meaningful way? This would be equivalent then to a frequentist confidence interval in a concept. We can do this in several different ways. The two main ways that we make Bayesian posterior intervals, or credible intervals, are equal-tailed intervals and highest posterior density intervals. In the case of an equal-tailed interval, we put an equal amount of probability in each tail. So to make a 95% interval, we'll put 0.025 in each tail. To be able to do this, we're going to have to figure out what the quantiles are. So we're going to need some value q. Say the probability theta is less than q in posterior, given y equals 1. Here we can get this by integrating from 0 to q, 2 theta d theta. And again, we'll see that's just q squared. So we can say an interval that goes from the square root of 0.025 to the square root of 0.975, and plugging in those numbers is going to be 0.158 to 0.987. Under the posterior, that will have probability 0.95. This is an equal-tailed interval in that the probability that theta is less than 0.158 is the same as the probability that theta is greater than 0.987. And we can say, under the posterior, there's a 95% probability that theta is in this interval. Another approach is what's referred to as highest posterior density, or HPD. Here we want to ask, where in the density is it highest? And so in this case, we want to say, well, about here are the highest levels, and so this interval is going to go between these 2 points. Theoretically, this will be the shortest possible interval that contains a given probability, in this case a 95% probability. We can see here that it's going to go all the way up to 1 just from the graph. So we're asking, what's the probability theta is bigger than some value? And looking at the quantiles again, that value is going to be the square root of 0.05. I should write that this is a posterior. And so we can say the probability theta is greater than 0.224 is 0.95. So this is the shortest possible interval that under the posterior has probability 0.95. It's theta going from 0.224 up to 1. Let's think about what we have here. The posterior distribution describes our understanding of our uncertainty, combining our prior beliefs and the data. We have a probability density function, so at the end of the day, we can make intervals and talk about probabilities of theta being in the interval. This is a much more satisfying approach than the frequentist approach, where we get confidence intervals, but we can't say a whole lot about the actual parameter relative to this confidence interval. We can only make long-run frequency statements about a lot of hypothetical intervals. In this case, we can legitimately say the posterior probability theta is bigger than 0.05 is 0.9975, or we believe there's a 95% probability that theta is in between 0.158 and 0.987. Frequentists can't do this. Bayesians represent uncertainty with probabilities. So the coin itself is a physical quantity. It may have a particular value for theta. It may be fixed, but because we don't know what that value is, we represent our uncertainty about that value with a distribution. And at the end of the day, we can represent our uncertainty, collect it with the data, and get a posterior distribution and make intuitive statements. How do we choose a prior? Our prior needs to represent our personal perspective, our beliefs, and our uncertainties. Theoretically, we're defining a cumulative distribution function for the parameter. So in particular, we're defining probability that theta is less than or equal to some value c for all possible c on the real line. So this is true for an infinite number of possible sets. We're defining probabilities. This isn't practical to do, and it would be very difficult to do coherently so that all the probabilities were consistent. In practice, we work with a convenient family that's sufficiently flexible such that a member of the family will represent our beliefs, and we can build in external information if available, such as previous experiments. Generally, if one has enough data, the information in the data will overwhelm the information in the prior, and so the prior is not particularly important in terms of what you get for the posterior. Any reasonable choice of prior will lead to approximately the same posterior. However, there are some things that can go wrong. Suppose we choose a prior that says the probability theta equals 1/2 equals 1, and thus the probability theta equals any other value is 0. If we do this, we'll see our posterior, f of theta given y, which is proportional to f of y given theta, f of theta, turns out to be just f of theta. Our data won't factor in if we only put probability 1 on a single point in our prior. We can also think of this prior as a point mass at 1/2, such as a Dirac delta function. So in the Bayesian context, events with prior probability 0 have posterior probability 0. Events with prior probability 1 have posterior probability 1. Thus, a good Bayesian will not assign probability 0 or 1 to any event that has already occurred or already known not to occur. A useful concept in terms of choosing priors is that of calibration of predictive intervals. So if we make an interval where we're saying we predict 95% of new data points will occur in this interval, it would be good if, in reality, 95% of new data points actually did fall in that interval. How do we calibrate to reality? This is actually more of a frequentist concept, but it is important for practical statistical purposes that our results do reflect reality. So we can compute a predictive interval. This is an interval such that 95% of new observations are expected to fall into it. So it's an interval for the data, for y or x, rather than an interval for theta, like we've been looking at. In particular, we can write this as f of y is the integral of f of y given theta times the prior f of theta d theta. We can also see this as integrating the joint density of y and theta, integrating out theta to get the marginal for y. So this is our prior predictive before we observe any data. Suppose we're going to flip a coin 10 times and count the number of heads we see. We're thinking about this in advance of actually doing it, so we're interested in the predictive distribution. How many heads do we predict we're going to see? This, of course, will depend on the coin itself. What's the probability it shows up heads? So we'll need to choose a prior. In terms of the number of heads, I can write x for the number of heads as x being the sum, as I goes from 1 to 10, of y sub I, where y is each individual coin flip, y1 through y10. If we think that all possible coins or all possible probabilities are equally likely, then we can put a prior for theta that's flat over the interval from 0 to 1. So now we can ask, what's our predictive distribution for the number of heads we'll see? X can take possible values 0, 1, 2, 3, up to 10. The predictive distribution, f of x, is going to be the integral of the likelihood, f of x given theta, times the prior, f of theta, d theta. So writing this out, we have a binomial likelihood. So we're going to integrate theta from 0 to 1. Binomial likelihood is 10 factorial over x factorial 10 minus x factorial times theta to the x, 1 minus theta to the 10 minus x, times our prior, 1 d theta. Note that because we're interested in x at the end, it's important that we distinguish between a binomial density and a Bernoulli density. So here we just care about the total count rather than the exact ordering, which would be Bernoulli's. For most of the analyses we're doing, where we're interested in theta rather than x, the binomial and the Bernoulli are interchangeable because the part in here that depends on theta is the same. But here we care about x for a predictive distribution, so we do need to specify that we're looking at a binomial because we're looking at counts. All right, how do we simplify this? This is an integral that might be sort of difficult to see immediately how to do. Let's recall some interesting pieces of math. First, recall that for an integer n, we can write n factorial is equal to gamma of n plus 1. The gamma function is a generalization of the factorial function and can be used for non-integers. The other thing is that if z follows a beta distribution with parameters alpha and beta, then the density for z, f of z, we can write as gamma of alpha plus beta over gamma of alpha times gamma of beta times z to the alpha minus 1 times 1 minus z to the beta minus 1. All right, so we're interested in a beta distribution here because we can simplify this piece to look like a beta distribution or beta density. So let's do a little simplification. We can write this 10 factorial as gamma of 11, and then write that as gamma of x plus 1 times gamma of 11 minus x, and then theta to the x plus 1 minus 1 times 1 minus theta to the 11 minus x minus 1 d theta. This may not look that much simpler, but it is closer to the beta density. Now if I just rearrange a little bit with the gamma terms, I can pull out this gamma of 11 and replace it with a gamma of 12. Now what I have inside the integral here is exactly a beta density, where the alpha parameter is x plus 1, and the beta parameter is 11 minus x. Because it's a beta density, we know all densities integrate up to 1. So this whole integral here is just 1. So we can write this as gamma of 11 over gamma of 12 times 1. Much easier way to do integrals. And then switching back to a factorial notation, gamma of 11 is 10 factorial, gamma of 12 is 11 factorial. So this whole thing simplifies to 1 over 11 for possible x values of 0, 1, 2, and so on up to 10. Thus we see that if we start with a uniform prior, we then end up with a discrete uniform predictive density for x. If all possible coins, or all possible probabilities, are equally likely, then all possible x outcomes are equally likely. What about after we've observed data? What's our posterior predictive distribution? So in this case, we can think about flipping a coin. We don't know what the probability it comes up heads is. But suppose we observe after one flip, we got a head the first time. We want to ask, what's our predictive distribution for the second flip, given that we saw a head on the first flip? So in this case, we can think about a posterior predictive distribution, f of y2 given y1. And so we can write that as the integral of f of y2 given theta and y1 times f of theta given y1 d theta. Again, we're integrating out theta, but this time we're going to use the posterior distribution for theta instead of the prior distribution for theta. In most cases, y2 we're treating as independent from y1, so that will imply that we can simplify this expression and just say it's y2 given theta times f of theta given y1 d theta. So again, you can see this looks very much like the prior predictive, except we're using the posterior distribution for theta instead of the prior distribution. As a particular example, again, suppose we're thinking of a uniform distribution for theta, and we observe the first flip, y1 equals 1. We get a heads. What do we predict for the second flip? This is no longer going to be a uniform distribution like it was in the first case, because we have some data. We have one head coming up on the first flip. So this gives us some information about the coin. We're now going to think it's more likely we're going to get a second head, because it's more likely that theta is at least 1/2 and possibly larger than 1/2. So let's compute this. F of y2 given y1 equals 1 is equal to the integral, in this case integral goes from 0 to 1, of theta to the y2, 1 minus theta to the 1 minus y2, times the posterior, which is 2 theta d theta. We can simplify this a bit to be 2 times theta to the y2 plus 1 times 1 minus theta to the 1 minus y2 d theta. We could work this out in a more general form, but in this case, y2 has to take the value 0 or 1. The next flip is either going to be heads or tails. So it's easier to just plop in a particular example. We can compute the probability y2 equals 1 given y1 equals 1. And so here we can just plug in a 1 for y2, and we get the integral from 0 to 1 of 2 theta squared d theta. And so doing that integration, we get a theta cubed, and this just works out to be 2/3. Thus, the complement, probably of getting a head, given we saw a tail the first time, is going to be 1/3. So we can see here that the posterior is a combination of the information in the prior and the information in the data. In this case, our prior is like having two data points, one head and one tail. Saying we have a uniform prior for theta is actually equivalent, in an information sense, to saying we have observed one head and one tail. And so then, when we do go ahead and observe one head, it's like we now have seen two heads and one tail. And so our predictive distribution, our posterior predictive distribution for the second flip says, well, if we have two heads and one tail, then we have probably 2/3 of getting another head and probably 1/3 of getting a tail. When we use a uniform prior for a Bernoulli likelihood, we get a beta posterior. Likelihood y given theta is sum of theta to the sum of the y sub i's, 1 minus theta to the n minus sum of the y sub i's. Our prior for theta is just a uniform, and thus our posterior for theta is the likelihood times the prior over the integral of the likelihood times the prior d theta, so that it integrates up to 1. So the likelihood, again, is theta to the sum of the y sub i's, 1 minus theta, n minus the sum of the y sub i's, times the indicator function for the prior. And then in the denominator, we just make sure that this integrates up to 1. Rather than try to work out this integral, we use the common trick of recognizing it as the kernel of a beta distribution. And so we'll rearrange the terms in here to make it be exactly a beta distribution so that this integral will be 1 and it will go away. Beta distributions have these gamma functions in them. And so here's what we're going to need to put in to make this all work out correctly. And so this integral now is going to be gamma of n plus 2 over gamma of sum of the y sub i's plus 1 times gamma n minus the sum of the y sub i's plus 1 times theta to the sum of the y sub i's, 1 minus theta, n minus the sum of the y sub i's, d theta. What we have here now is a beta distribution, and so it integrates up to 1. And thus, this whole expression simplifies to gamma n plus 2 over gamma sum of the y sub i's plus 1 times gamma n minus the sum of the y sub i's plus 1 times theta to the sum of the y sub i's, 1 minus theta to the n minus the sum of the y sub i's, times the indicator function that theta is between 0 and 1. Thus we see the posterior for theta, given y, follows a beta distribution with parameters sum of the y sub I plus 1 and n minus the sum of the y sub i's plus 1. In fact, the uniform distribution is the beta 1, 1, and any beta distribution is conjugate for the Bernoulli distribution. Any beta prior will give a beta posterior. Recall the beta prior looks like f of theta is gamma of alpha plus beta over gamma of alpha, gamma of beta, times theta to the alpha minus 1, 1 minus theta to the beta minus 1, over the interval from 0 to 1. Thus, we can look at the posterior for theta given y. This is proportional to the likelihood times the prior, which is theta to the sum of the y sub i's, 1 minus theta to the n minus sum of the y sub i's times this prior, gamma of alpha plus beta, over gamma of alpha, gamma of beta, theta to the alpha minus 1, 1 minus theta to the beta minus 1 over the interval as theta goes from 0 to 1. In terms of proportionality, we only need to keep the things that have thetas in them so we can drop this normalizing constant and collect the theta terms. Theta plus sum of the y sub i's minus 1, 1 minus theta to the beta plus n minus sum of the y sub i's minus 1 over the interval from 0 to 1. We thus see this is a beta distribution, so theta given y follows a beta distribution with parameters alpha plus sum of the y sub i's and beta plus n minus the sum of the y sub i's. When alpha and beta are both 1, as in the uniform distribution, we get the result that we had earlier. But this whole concept now of starting with a beta prior and getting a beta posterior is a really convenient one. This whole process, where we choose a particular form of prior that works with the likelihood, is called using a conjugate family. A family of distributions is referred to as conjugate if when you use a member of that family as a prior, you get another member of that family as your posterior. The beta distribution is conjugate for the Bernoulli distribution. It's also conjugate for the binomial distribution. The only difference in the binomial likelihood is that there's an n choose x combinatoric term. Since that does not depend on theta, then we get the same posterior. We often use conjugate priors because they make life much more simple. As we're working out posteriors, if we can't recognize this form, we get some intractable integral in the denominator, and trying to work out that integral can be problematic. It can get complicated really quickly. So sticking to conjugate families allows us to get closed form solutions. If the family is flexible enough, then you can find a member of that family that closely enough represents your beliefs. We can represent this model as a hierarchy. The observations y1 through yn follow a Bernoulli likelihood. Theta is our primary parameter. It depends on alpha and beta, and we give theta a beta prior. Alpha and beta, we might give particular values, alpha naught and beta naught. We refer to alpha and beta as hyperparameters. Typically, what we'll be doing here is we'll set these equal to particular values. But in a more complicated problem, you might also want to have more flexibility by putting priors on alpha and or beta. We can thus extend this hierarchy to more levels. In complicated problems, this may provide some added value and added flexibility. In simple problems, this tends to be more work without providing much additional value. So these sorts of hierarchical models will be beyond the scope of this course. Returning to the model where we have a Bernoulli likelihood with n observations, or a binomial likelihood, and using a beta prior, we get a posterior, which is a beta alpha plus sum of the y sub i's, beta plus n minus sum of the y sub i's. Here it is clear how both the prior and the data contribute to the posterior. For a prior, which is a beta alpha beta, this is equivalent to having alpha plus beta additional observations. We can say this is the effective sample size of the prior. And we'll see how this is so in the next calculation. recall that the expected value, or mean of a beta, is its first parameter over the sum of the parameters. So in the case of our posterior here, its posterior mean is alpha plus sum of the y sub i's divided by alpha plus sum of the y sub i's plus beta plus n minus sum of the y sub i's. We can then write this, simplifying as alpha plus sum of the y sub i's over alpha plus beta plus n. This can further be decomposed as alpha plus beta over alpha plus beta plus n times alpha over alpha plus beta plus n over alpha plus beta plus n times sum of the y sub i's over n. What we see here is that we get the posterior mean is equal to a prior weight times the prior mean plus a data weight times the data mean. So the mean of the data is the sum of the y sub i's over n. The prior mean is alpha over alpha plus beta. The weight for the prior and the weight for the data add up to 1. So they are weights. And so the posterior mean is a weighted average of the prior mean and the data mean. We can also see here, here's the n for our sample size. And so the corresponding term over here tells us the effective sample size of the prior. Thus, the effective sample size of the prior for a beta prior on a Bernoulli or binomial likelihood is alpha plus beta. This effective sample size also gives you an idea of how much data you would need to make sure that your prior doesn't have much influence on your posterior. If alpha plus beta is small compared to n, then the posterior will largely just be driven by the data. If alpha plus beta is large relative to n, then your posterior will be largely driven by the prior. Thinking about intervals, recall that a frequentist 95% confidence interval for theta is theta hat plus or minus 1.96 times the square root of theta hat 1 minus theta hat over n. Now as a Bayesian, we can make a 95% credible interval using our posterior distribution for theta. We would use a computer package, such as R, to numerically find the values for the interval. We can find an interval that actually has 95% probability of containing theta, and this is a true probability statement. For a confidence interval, we can't make a probability statement that theta is in the interval. Sequential analysis is also straightforward in Bayesian statistics. Suppose we start with a prior, f of theta, and we observe n data points. We observe y1 through yn. We then update our prior. We get a posterior theta given y1 through yn. So far, so good. Then suppose you come in the next day and you observe more data. We observe m more data points, yn plus 1 through yn plus m. Now that we have more data, can we update again? And indeed we can. We treat yesterday's posterior as today's prior. So we now use theta given y1 through yn as our prior, update it with data, and get a new posterior, theta given y1 through yn plus m, all of the data. And so we can just chain these together, doing a sequential update every time we get new data. We can get a new posterior, and we just use our previous posterior as the prior to do another update using Bayes' theorem. In this way, we actually get the same answer mathematically as if we started with the prior and then all the data came at once and we did a single update with Bayes' theorem. We will get the exact same posterior. So in the Bayesian paradigm, this is consistent whether we're doing sequential updates or we do a single batch update. This is very different from the frequentist scenario where you can't do sequential updates in this way and you get different answers depending upon when you observe your data and how you combine them. One of the earlier areas where Bayesian statistics was accepted under government regulation was in the medical device testing area, and this is because of its ability to do sequential updates. With medical devices, you often have very small sample sizes, but you're only making minor updates to the devices and you're doing new trials. The ability of Bayesian statistics to do easy sequential updates made it very practical and appealing for the medical device testing industry.
This segment will look at using R for exploring the beta binomial conjugate analysis and working with binomial and beta distributions in R. Suppose we were giving two students a multiple choice exam with 40 questions, where each question has 4 choices. We don't know how much the students have studied for this exam, but we think that they will do better than just guessing randomly. So here up in the comments section, I'm giving you the background and we'll pose 7 questions. First, what are our parameters of interest? Next, what is our likelihood? What prior should we use? For this prior, for theta, we can ask what's the prior probability that theta is greater than 1/4, which would be guessing randomly, theta is greater than 1/2, or theta is greater than 0.8. Now suppose the first student takes the test and gets 33 of the 40 questions right. Calling their parameter theta1, we can ask what's the posterior distribution for their parameter, and what's the posterior probabilities that will be greater than 1/4, 1/2, or 0.8. What's a 95% posterior credible interval for this parameter? Now thinking about the second student, suppose they get 24 questions right. What's the posterior distribution for that parameter? What's the posterior probability it's greater than 1/4, 1/2, or 0.8? And what's a 95% credible interval for it? Finally, what's the posterior probability that theta1 is greater than theta2, that the first student has a better chance of getting a question right than the second student? All right, we'll move on to solutions. The first two are more just theory. Our parameters of interest are theta1 being the true probability that the first student will answer a question correctly, and theta2 being the true probability the second student will answer a question correctly. We're going to use a binomial likelihood with n equals 40, and then probabilities theta, either theta1 or theta2. And this is assuming that each question is independent and that the probability a student gets each question right is the same for all questions for that student. What prior should we use? The conjugate prior for a binomial likelihood is a beta prior. The information we have is that we think they will do better than just guessing randomly, so the prior mass should be largely above 0.25. We'll want a prior mean bigger than 1/2, maybe say 2/3. So what I'm going to do is I'm going to make a sequence of possible theta values that goes from 0 to 1 in increments of 1/100th. And then we can plot some different beta priors. We can start by plotting the default prior, which is a uniform, or a beta 1/1. So here's our default uniform prior. All values, probabilities between 0 and 1 are equally likely, but this does not encode our belief that we think they're going to do better than just guessing randomly. So let's try a beta distribution that has prior mean 2/3. For example, a beta distribution with parameters 4 and 2. So now we can see we're moving most of the mass higher. although there's still some mass down here below 0.25. As we increase the parameter values, that increases the effective sample size and concentrates the distribution. So let's try a beta distribution with parameters 8 and 4, which still maintains a prior mean of 2/3. This distribution now is more concentrated, and you can see pretty much all the mass is between 0.25 and 1. So this seems like a reasonable distribution to use as a prior for this problem. We can now ask, what are the prior probabilities that the parameter will be bigger than 1/4, 1/2, or 0.8? We can use the p-beta function. P-beta gives us the cumulative distribution function for the beta distribution. That's a probability it's less than or equal to that value. So because we're asking probably it's greater than, we'll take 1 minus the p-beta function. We can see the probability it's greater than 0.25 is 0.9988, almost 1. The probability it's greater than 1/2 is 0.887. The probability it's greater than 0.8 is 0.16. Okay, those are prior probabilities. Now suppose we collect some data and the student gets 33 of the 40 questions right. What's our posterior distribution? The posterior distribution will be beta with parameters 8 plus 33 and 4 plus 40 minus 33, or a beta 4111. The posterior mean is alpha over alpha plus beta. We can also compare that to the maximum likelihood estimate. Posterior mean is 0.788, and the maximum likelihood estimate is 0.825. So the posterior mean is somewhere in between the maximum likelihood estimate and the prior mean of 2/3. We can plot this. Let's add to the plot of the prior, we'll add in the posterior distribution, posterior density. As we try to do that, we see that the posterior density is on a different scale and it goes off the top of the chart. So if we plot that one first, R will make the y-axis appropriately sized, and we can put them both on the same plot. So we'll do that in the other order. We'll plot the posterior first, and then we'll add lines with the prior. In this case, I'm going to change the line type to make it a dashed line. LTY2 gives us a dashed line for the prior. So here the dashed line shows the prior, and the solid line shows the posterior. As we get more information, the distribution gets more concentrated. We'd also add the likelihood to this. LTY3 will be a dotted line. We'll add a dotted line for the likelihood. Turns out the likelihood is on a different scale. We're going to need to rescale it because it doesn't have the same type of normalizing constant to make it a density. So it doesn't have to be on the same scale. So we're going to rescale it just so we can plot it on the same plot. In this particular case, I've tried this in advance, and the number 44 works as a good scaling factor. So I'm just going to multiply it by 44 in order to have a pretty plot here. So now the dotted line is the likelihood, the solid line is the posterior, and the dashed line is the prior. You can see that posterior is in between the prior and the likelihood. It's closer to the likelihood because in this case there's more information in the likelihood. Recall that we have 40 samples in the likelihood, and we have a prior with an effective sample size of 8 plus 4 is 12. And so it makes sense that the posterior will be closer to the likelihood than to the prior. How about posterior probabilities? Posterior probability that theta will be greater than 1/4, 1/2, or 0.8. Posterior probability that theta 1 is greater than 1/4 is 1 to double precision. And the probability it's greater than 1/2 is almost 1. Probability it's greater than 0.8 is now up to 0.4444. Given that our data had a value bigger than 0.8, we have a fair amount of confidence that theta 1 is a larger value now. what would be an equal-tailed 95% credible interval? We can use the Q beta function to get the quantiles from the beta distribution and see that there's a 95% posterior probability that theta 1 is in between 0.669 and 0.887. And that's consistent with the plot here. Most of the mass is between 0.669 and 0.887. All right, now thinking about a second student. Second student gets 24 out of 40 questions right. Their theta 2 now will have a posterior that has a beta distribution with parameters 32 and 20. Get the posterior mean and the maximum likelihood. Again, our prior mean was 2/3. The maximum likelihood estimate is 0.6, and the posterior mean is somewhere in between at 0.615. We see a similar story when we plot these. Here the prior is this dashed line, centered at 2/3. The likelihood is the dotted line at 0.6, and then the posterior is the solid line in between the two, closer to the likelihood. You can see the posterior mass is all sort of between 0.45 and 0.8. Indeed, if we ask what's the posterior probabilities of it being greater than a quarter, a half, or 0.8, we see that posterior probability close to 1 of being greater than a quarter, probability of 0.95 of being greater than a half, but probability very small, 0.00125 of being greater than 0.8. Again, consistent with the plot. A 95% equal-tailed credible interval for theta 2. That goes from 0.48 to 0.74. So this is smaller values than for the first student, which makes sense because the second student didn't get as many questions right. Now this interval here does in fact overlap with the 95% credible interval for the first student. So there is some overlap, but they're centered very differently. So our final question was, what's the probability that theta 1 is greater than theta 2? This would be difficult to do in closed form, so we're going to do it by simulation. We're going to draw 1,000 samples from each posterior distribution and see how often we observe theta 1 greater than theta 2. So I'll use the R beta function to generate random samples from the first beta distribution and from the second beta distribution, and then we'll look at whether theta 1 is greater than theta 2. R will evaluate this statement as an indicator function, so it will be 1 when it's true and 0 when it's false. So if we take the average of those indicator functions, that will give us an empirical probability that theta 1 is greater than theta 2. So we can see here our empirical probability came out to be 0.967. So the probability is close to 1, but not completely certain that theta 1 is greater than theta 2. In some of the exercises later in this course, you'll be asked to work with other distributions, including gamma distributions and normal distributions. And you can see that there are equivalent functions in R for the gamma distribution and the normal distribution. This segment will look at a binomial beta conjugate analysis using Excel and looking at using Excel for questions about distributions. Up at the top of this file, I've posed a scenario and some questions. Suppose we're giving two students a multiple choice exam with 40 questions, where each question has 4 choices. We don't know how much the students have studied for this exam, but we think that they will do better than just guessing randomly. Based on the scenario, we can ask a number of questions. What are the parameters of interest? What is our likelihood? What prior should we use? What is the prior probability that theta parameter would be greater than 1/4, 1/2, or 0.8? Suppose the first student gets 33 of 40 questions right. If they have parameter theta1, what's the posterior distribution for this parameter? What's the posterior probability that it's greater than 1/4, 1/2, or 0.8? And what's the 95% credible interval for it? Suppose the second student gets only 24 questions right. What's the posterior distribution for their parameter? What's the posterior probability it's greater than 0.25, 0.5, or 0.8? And what's the 95% posterior credible interval for it? And finally, what's the posterior probability that theta1 is greater than theta2? That is, the first student has a better chance of getting a question right than the second student. First two questions are more theoretical questions. Our parameters of interest are theta1 being the true probability the first student will answer a question correctly, and theta2 being the true probability the second student will answer a question correctly. We're going to use a binomial likelihood with parameters n equals 40 and the probability given by the appropriate theta. Here we're assuming that each question is independent and that the probability a student gets each question right is the same for all questions for that student. Now, how do we decide what prior we should use? For a binomial likelihood, the conjugate prior is a beta prior. Let's explore some possible beta priors. I'm going to set up some columns here in the spreadsheet so then we can look at plots of possible beta priors. So in column B, I'm going to have possible values for theta. We'll look at the prior distribution, f of theta. We'll be looking at the likelihood for theta1, the posterior for theta1, the likelihood for theta2, and the posterior for theta2. For theta, we're going to have values going from 0.01 up to 0.99. We can use the fill function, edit fill series, to go down the column in increments of 0.01, going up to a value of 0.99. I'm going to set this up so that we've got some flexibility in the formula, and the two parameters for the beta distribution are often called alpha and beta. And let's start with the standard uniform distribution, the default prior, so that's values 1 and 1 in our prior beta distribution. Prior density we can stick into column C. There isn't a built-in function in Excel for a beta density, so we'll write this out by hand using the factorial function to get the gamma functions. We'll paste this in to the first cell, and then we'll copy it to the remaining cells. We can now plot this using a line plot. This is a uniform distribution. All probabilities between 0 and 1 are equally likely. It's a standard default distribution for a prior, but it doesn't encode our information, in this case, that we think they will do better than just guessing randomly. So we need a prior that will put its mass above 0.25. For example, we might think that our prior probability should be 2/3. So let's consider some possibilities for priors with prior mean 2/3. One example would be an alpha of 4 and a beta of 2. So now, because I've set it up as a formula, Excel automatically updates it and updates the plot. You can see here the mass has moved to higher probabilities, but at 0.25 there's still a fair amount of probability that's below 0.25. So the larger we make these parameter values, the more concentrated the distribution gets. Let's try something a little more concentrated, for example, 8 and 4. This is now looking good, because at 0.25, there's very little probability that this distribution is below 0.25, and it's fairly nicely spread between 0.25 and 1. So for the rest of this piece, we'll use a prior distribution that's a beta with parameters 8 and 4. Let's find the probabilities that the prior distribution will be above 0.25, 0.5, or 0.8. We can use the beta dist function. This is the cumulative distribution function for a beta distribution. Recall that cumulative distribution is the probability that the distribution is less than or equal to that value. So if we want a greater than, we'll take 1 minus. So the prior probability that a theta will be greater than 1/4 is 0.9988, almost 1. Probability that it's greater than a half is 0.887, and the probability that it's greater than 0.8 is 0.16. Now suppose the first student takes the exam and gets 33 of 40 questions right. The posterior distribution will be a beta distribution with parameters 8 plus 33 and 4 plus 40 minus 33, or 41 and 11. We can think about what are the posterior mean and maximum likelihood estimates. Posterior mean for theta 1 is 0.788. The maximum likelihood estimate is 0.825. Recall the prior mean is 2/3, and so you can see that the posterior mean is in between the prior mean and the data estimate, or maximum likelihood estimate. Let's go ahead and plot the likelihood and the posterior. The likelihood, we can get the binomial distribution, and in Excel, we can get the density by setting the cumulative equals false. The posterior density is another beta distribution, and that one we'll need to calculate by hand. I'll now take these two values and copy them down into the rest of the chart. So now I can plot the likelihood and plot the posterior. I'm putting them on different charts because they're on different scales, and so they don't show up well all in the same chart. But we can line them up nicely here and see that, in fact, the posterior is close to the likelihood and in between the likelihood and the prior. The posterior is closer in shape and location to the likelihood because the likelihood has more information in it. Recall here we have 40 data points in the likelihood, and the prior has an effective sample size of 8 plus 4, or 12. So there's more information in the likelihood than there is in the prior, and thus the posterior looks more like the likelihood than it looks like the prior, but is somewhere in between. The posterior probabilities that theta 1 is greater than 1/4, a half, or 0.8 those are essentially 1, 0.99999, and 0.4444. You can see that the mass is accumulated up here between 0.6 and 0.9 or so. And so we're almost certain that theta 1 is greater than a half, and there's a reasonable chance it's greater than 0.8, which is a big change from the prior. We can look at an equal-tailed 95% credible interval. Using the beta inverse function, and we can see that there's a 95% posterior probability that the true value of theta 1 is in between 0.669 and 0.887. And that makes sense relative to this plot. Now let's consider the second student. Second student got only 24 of 40 questions right, and so their posterior distribution will be a beta with parameters 32 and 20. We can look at the posterior mean and the maximum likelihood estimate for theta 2. Recall the prior mean is 2/3. The posterior mean is 0.615. The maximum likelihood estimate is 0.6. So again, here they're all closer, but the posterior mean is in between the likelihood or data estimate and the prior estimate. We can put the likelihood for theta 2 into column F here, and put the posterior for theta 2 in column G. Now take these, and we'll paste it down in the spreadsheet, and we'll make plots of them as well. The likelihood for theta 2 and the posterior for theta 2. So in this case, the posterior is a little bit lower than it was for theta 1, which makes sense because the second student didn't get as many questions right. Again, it's much closer to the likelihood than it is to the prior, but the posterior is in between. And you can see that it's going roughly from about 0.45 to 0.8. So we can again ask questions, what are the posterior probabilities that theta 2 is greater than 1/4, 1/2, or 0.8? As well as what's a 95% credible interval for theta 2. We can see posterior probability it's greater than 1/4 is essentially 1. There's a 95% probability that it's greater than 1/2, but the probability that theta 2 is greater than 0.8 is very small, 0.00125. That makes sense from the picture. Theta 2 is not likely to be as large as theta 1. 95% credible interval goes from 0.48 to 0.74. It is worth noting that this credible interval does overlap with the credible interval for theta 1. So what is the posterior probability that theta 1 is greater than theta 2? Well, we can do this by drawing random samples from each of them and see how often we observe theta 1 greater than theta 2. So let's put theta 1 in column H and theta 2 in column I. We'll draw some random samples here. Oops. I'm going to draw samples using the inverse CDF method for drawing random values. So I'm going to draw a random uniform, put it into the beta inverse function, and that will give me a draw from the beta distribution. For theta 2, same idea except with different beta parameters. And finally, I'm going to ask, is theta 1 larger than theta 2? So I'm going to set up an indicator function for theta 1 larger than theta 2 and put that into column J. Now we can take this and copy this formula down and fill up 500 rows of this. And we'll use that to estimate by simulation. So this is a Monte Carlo experiment, and we'll just estimate using the empirical probability that theta 1 is greater than theta 2. So we'll get 500 samples, and then for the indicator functions, we'll add up all 500 of them, divide by 500, and that will give us an empirical estimate of the probability that theta 1 is bigger than theta 2. So here we have 500 theta 1 values, 500 theta 2 values, and then our indicator functions. And you can see in almost all cases, theta 1 is greater than theta 2, but there are some cases where theta 1 is less than theta 2. So this number is going to be close, this probability will be close to 1, but it won't be exactly 1. So we'll scroll down, stick in a sum, divide that by 500, and see we get an empirical estimate of 0.98. And so we can say that we think the posterior probability theta 1 is greater than theta 2 is approximately 0.98. In some of the exercises later in this course, you'll be asked to work with other distributions besides the binomial and the beta. And so in Excel, there are functions for the gamma distributions and for normal distributions as well. Let's consider Poisson data. For example, think about chocolate chip cookies. In mass-produced chocolate chip cookies, they make a large amount of dough, they mix in a large number of chips, mix it up really well, and then chunk out individual cookies. In this process, the number of chips per cookie approximately follows a Poisson distribution. If we were to assume that chips have nose volume, then this would be exactly a Poisson process and follow exactly a Poisson distribution. But in practice, chips are not that big, and so they follow approximately a Poisson distribution for number of chips per cookie. So if we model the number of chips per cookie, y sub I, as Poisson with mean lambda, we can have a likelihood for a bunch of observations y, given lambda, to be lambda to the sum of the y sub i's times e to the minus n lambda over the product of y sub I factorial. For this, we need lambda to be positive valued. Okay, now our parameter has to be positive valued. What type of prior should we put on lambda? It would be convenient if we could use a conjugate prior. So we can ask, what distribution looks like lambda to the something e to the minus something lambda? That distribution is the gamma distribution. So a gamma prior for lambda is going to look like lambda being a gamma prior with parameters alpha and beta. F of lambda is beta to the alpha over gamma of alpha times lambda to the alpha minus 1 e to the minus beta lambda for lambda greater than 0. Thus the posterior, f of lambda given y, will be proportional to the likelihood, f of y given lambda, times the prior, f of lambda. And this is proportional to lambda to the sum of the y sub i's, e to the minus n lambda, times lambda to the alpha minus 1, e to the minus beta lambda. Under the proportionality, we only need to focus on the terms that contain lambda, so we can drop these normalizing constants. This then simplifies to lambda to the alpha plus sum of y sub i's minus 1, e to the minus beta plus n lambda. Thus we can see the posterior is a gamma distribution with parameters alpha plus sum of the y sub i's and beta plus n. Recall that the mean of the gamma of a gamma random variable is its first parameter over its second parameter under this parameterization. Do note that there are a lot of different parameterizations of gamma random variables out there, and they may have different parameterizations of the mean as a result. So in this case, we can see the posterior mean is going to be alpha plus sum of the y sub i's over beta plus n. We can then rewrite this as beta over beta plus n times alpha over beta plus n over beta plus n times sum of the y sub i's over n. So we can see that in this case as well, our posterior mean is a weighted average of the prior mean and the data mean. The weights add up to 1. With the n here, this is clearly the sample size for the data, and so the effective sample size for the prior in this case is beta. We can now ask, how would we choose our parameters, our hyperparameters alpha and beta. If we're trying to specify a prior for this, and we're thinking about something concrete like cookies, how would we choose values for alpha and beta in order to be able to do this problem and get a posterior after we've observed data? How would we choose a particular prior, in particular alpha and beta, we need to specify values for? In the case of something concrete like chocolate chip cookies, we may have some ideas about what is in our prior and how to specify information for our prior. What type of strategies would we use to put that information in, then collect data and update it to get a posterior? Let me present two strategies. Under the first strategy, we want to include information into our prior based on our personal knowledge. We can start by thinking about what does the prior mean. The prior mean in this case is alpha over beta. And so we can think, what do we think our prior mean is for the number of chips per cookie? What do we think the number of chips per cookie on average is? That would be our prior mean. The strategy now involves we have to specify a second thing because there are two parameters. So if we specify two things, we can solve for alpha and beta. One possible second thing we could specify is our prior standard deviation or our prior variance. This is how sure are we about our information in our prior mean. If we think the prior mean is that there are 12 chips per cookie, do we think there's a standard deviation of 3, standard deviation of 4, of 6? How sure are we? We can specify a prior standard deviation, and that would be square root of alpha over beta. Given these two quantities, we can solve for alpha and beta, and that will give us our gamma prior. Another way of specifying our confidence or our uncertainty in our prior is to think about the effective sample size. As we see here, the effective sample size is beta. And so we can specify how many units of information we think we have in our prior, how sure we are in that sense, versus how confident we'll be when we have n more data points. And so we can specify a value for beta, and we can specify a prior mean and solve for alpha. This would be a way, two different ways, to specify alpha and beta, and to get a prior to move forward. Another approach is that we can represent ignorance with a vague prior. In Bayesian statistics, a vague prior refers to one that's relatively flat across much of the space. In this case, we can think about some small epsilon. So epsilon is some small number that is strictly positive, and then we can have a gamma prior with parameters epsilon and epsilon. As long as these are both strictly positive, this is a proper prior, it's a proper distribution. In this case, then, the mean will be epsilon over epsilon, which is 1, but its variance will be huge, essentially 1 over epsilon. If epsilon is small, there'll be a really big variance, and so this will be a very diffuse prior across the whole space. If we think about what the posterior mean looks like under this prior, the posterior mean would be epsilon plus the sum of the y sub i's over epsilon plus n. If epsilon is really small, then this is approximately the sum of the y sub i's over n, just the data mean. And thus, the posterior will be largely driven by the data, and the prior will have very little influence. Let's consider the case of exponential data. For example, suppose you're waiting for a bus that you think comes on average once every 10 minutes, but you're not sure exactly how often it comes. We'll say y follows an exponential distribution with rate lambda. Your waiting time has a prior expectation of 1 over lambda. It turns out the gamma distribution is conjugate for an exponential likelihood. Gamma is actually our conjugate for a number of different things. We need to specify a prior, so a particular gamma, in this case. If we think that the buses come on average every 10 minutes, that's a rate of 1 over 10. So our prior mean should be 1/10. Thus, we'll want to specify a gamma distribution whose first parameter divided by second parameter is 1/10. We can think then about
our variability, perhaps we want to specify a prior, which is a gamma 100, 1000. This will indeed have prior mean of 1/10, and it'll have a prior standard deviation of 1/100. Thus, if we think as a rough approximate of a mean plus or minus 2 standard deviations as a rough interval for our prior, we would say we're looking at 0.1 plus or minus 0.02 as a possible range for this rate parameter. So here's a particular prior we could specify. Suppose that we wait for 12 minutes and a bus arrives. Now you want to update your posterior for lambda about how often this bus will arrive. Posterior for lambda given y is proportional to the likelihood times the prior. This case, that's lambda e to the minus lambda y, lambda to the alpha minus 1, e to the minus beta lambda. Doing a little bit of simplification, we get lambda to the alpha plus 1 minus 1, e to the beta plus y lambda, negative. I'm writing this as alpha plus 1 minus 1 so that it is in the form of a gamma distribution. We can now say that lambda given y, the posterior, follows a gamma distribution with parameters alpha plus 1 and beta plus y. Plugging in our particular prior thus gives us a posterior for lambda, which is a gamma with parameters 101 and 1012. Thus, our posterior mean is going to be 101 over 1012. This is equal to 0.0998, or approximately 1 over 10.02. This one observation doesn't contain a lot of data under this likelihood. Our prior has a fair amount of information in it, and so our posterior doesn't shift a whole lot. When the bus comes and it takes 12 minutes instead of 10, it barely shifts our posterior mean up. It shifts it up a little bit, so we now think our expected waiting time is slightly more than 10 minutes, but not much more. One data point doesn't have a big impact here. The last distribution I'll talk about is the normal distribution, also known as the Gaussian distribution. The normal distribution arises in a wide variety of contexts, including heights of people, manufacturing industrial processes, and as a result of the central limit theorem. For now, let's suppose the standard deviation or variance is known and we're only interested in learning about the mean. This is a situation that often arises in monitoring of industrial production processes. So we'll say the x sub i's are IID normal with unknown mean mu and known variance sigma naught squared. How would we choose a prior for mu? We'd like to use a conjugate prior. It would be convenient. It turns out the normal is conjugate for itself, for its mean parameter. So we'll specify a prior for mu, which is normally distributed with some mean m naught and some variance s naught squared. I'm putting on naughts to specify particular values in this case, that these are not parameters. The posterior then, mu, given data x, that will be proportional to the likelihood times the prior. I'm not going to go through all the calculations here. I'll leave that to the supplementary material because it's fairly extensive and involves completing the square. At this point, I will just jump to the final result, which is that the posterior for mu given x follows a normal distribution, and its mean is nx bar over sigma naught squared plus m naught over s naught squared all over n over sigma naught squared plus 1 over s naught squared. And it has variance 1 over
n over sigma naught squared plus 1 over s naught squared. This is a somewhat complicated expression, but let's take a little closer look at the posterior mean. This posterior mean we can rewrite as n over sigma naught squared over n over sigma naught squared plus 1 over s naught squared times x bar plus 1 over s naught squared over n over sigma naught squared plus 1 over s naught squared times m. A little bit of simplification will give us n over n plus sigma naught squared over s naught squared times x bar plus sigma naught squared over s naught squared over n plus sigma naught squared over s naught squared times m. Thus we see that the posterior mean is a weighted average of the prior mean and the data mean, and indeed that the effective sample size for this prior is the ratio of the variance for the data to the variance in the prior. This makes sense because the larger the variance of the prior, the less information that's in it. The smaller the variation of the prior, the more information that's in it. We can also consider the case that both mu and sigma squared are unknown. If both mu and sigma squared are unknown, we can specify a conjugate prior in a hierarchical fashion. The data, x sub I, given mu and sigma squared, we represent as independent identically distributed normals with mean mu and variance sigma squared. We then specify a prior for mu conditional on a value for sigma squared to be normal with mean m and variance sigma squared over w. It depends on sigma squared. In this case here, w is going to be the ratio of sigma squared and some variance for the normal distribution. This is the effective sample size of the prior. Finally, the last step is to specify a prior for sigma squared. The conjugate prior here is an inverse gamma distribution, and we give it parameters alpha and beta. Lots of calculations later, we can get a posterior. Sigma squared, given x, follows an inverse gamma distribution with parameters alpha plus n over 2 and beta plus 1/2 times the sum of x sub I minus x bar squared plus n times w over 2 times n plus w times x bar minus m squared. The posterior distribution for mu, given sigma squared, follows a normal distribution with mean n x bar plus wm over n plus w and variance sigma squared over n plus w. So it explicitly depends on sigma squared. Note that this posterior mean can be written as the weighted average of the prior mean and the data mean. Again, we see that W is the effective sample size in this prior. In some cases, we really only care about mu at the end of the day. We want inference on mu, and we may want it such that it doesn't depend on sigma squared. We can marginalize out sigma squared, integrating it out, and at the end of the day, we get a posterior for mu, marginally, that follows a t-distribution. Similarly, the posterior predictive distribution also is a t-distribution. Finally, I note that we can extend this in various directions. This is going to be extended to the multivariate normal case that requires vector and matrix notation. This can also be extended in a hierarchical fashion if we want to specify priors for any of m, w, alpha, and beta. So far, we've seen examples of choosing priors that contain a significant amount of information. We've also seen some examples of choosing priors where we're attempting to not put too much information in to keep them vague. Another approach is referred to as objective Bayesian statistics, or inference, where we explicitly try to minimize the amount of information that goes into the prior. This is an attempt to have the data have maximal influence on the posterior. We sometimes refer to these as non-informative priors. For example, let's go back to coin flipping, where our data come from a Bernoulli distribution with unknown parameter theta. How do we minimize our prior information in theta? One obvious intuitive approach is to say that all values of theta are equally likely. So we could have a prior for theta, which follows a uniform distribution on the interval 0, 1. Saying all values of theta are equally likely seems like it would have no information in it. Recall, however, that a uniform 0, 1 is the same as a beta 1, 1. The effective sample size of a beta prior is the sum of its two parameters. So in this case, it has an effective sample size of 2. This is equivalent to data with one head and one tail already in it. So this is not a completely non-informative prior. We could think about a prior that has less information. For example, a beta 1/2, 1/2. This would have only half as much information, has an effective sample size of just 1. We can take this even further. Think about something like a beta 0.001, 0.001. This would have much less information, have a sample size fairly close to 0. In this case, the data would determine the posterior, and there would be very little influence from the prior. Can we go even further? In fact, we can. We can think of the limiting case. Something that we could think of as a beta 0, 0. What would that look like? Well, in this case, we could say its density is proportional to theta to the minus 1, 1 minus theta to the minus 1. This is not a proper density. If you integrate this over 0 to 1, you'll get an infinite integral. So it's not a true density in the sense of integrating to 1. There's no way to normalize it. It has an infinite integral. This is what we refer to as an improper prior. It's improper in the sense that it doesn't have a proper density, but it's not necessarily improper in the sense that we can't use it. If we collect data, we use this prior, and as long as we observe at least one head and at least one tail, or one success and one failure, then we can get a posterior, f of theta given y, which is proportional to theta to the y minus 1, 1 minus theta, to the n minus y minus 1. This you'll recognize as a beta distribution with parameters y and n minus y. Its posterior mean will be y over n. This you should recognize as theta hat the maximum likelihood estimate, the MLE. So by using this improper prior, we get a posterior which gives us point estimates exactly the same as the frequentist approach. But in this case, we can also think of having a full posterior. And so if we want to make interval statements, probability statements, we can actually find an interval and say that there's 95% probability that theta is in this interval, which is not something you can do under the frequentist approach, even though we may get the exact same interval. Key concepts here that I want to state in terms of using improper priors. The first is that improper priors are okay as long as the posterior itself is proper. There may be some mathematical things that need to be checked, and you may need to have certain restrictions on the data. In this case, we need to make sure that we observe at least one head and one tail to get a proper posterior. But as long as the posterior is proper, we can go forward and do Bayesian inference even with an improper prior. The second point is that for many problems, there does exist a prior, typically an improper prior, that will lead to the same point estimates as you would get under the frequentist paradigm. So we can get very similar results that are fully dependent on the data, under the Bayesian approach. But in this case, we can also continue to have a posterior
and make posterior interval estimates and talk about posterior probabilities of the parameter. Another example is thinking about the normal case. So think about y sub I being IID, normal with mean mu and variance sigma squared. Let's start off by assuming that sigma squared is known, and we'll just focus on the mean mu. We could think about a vague prior. Say mu is normally distributed with mean 0 and variance 1,000,000 squared. That would just spread things out across the line, the real line. You can take a wide variety of possible values. That would be fairly non-informative across a lot of possibilities. We can then think about taking the limit. What happens if we let the variance go to infinity? In that case, we're basically spreading out this distribution across the entire real line. And so we could say we have a density which is proportional to 1. It's just constant across the whole real line. Clearly, this is an improper prior, because if you integrate the real line, you get an infinite answer. However, if we go ahead and plug this into finding a posterior, f of mu given y is proportional to f of y given mu, f of y. The likelihood here is proportional to e to the minus 1 over 2 sigma squared, sum of y sub I minus mu squared, and our prior is just 1. So this is just the likelihood that we recover here, which we can simplify to be e to the minus 1 over 2 sigma squared over n, mu minus y bar quantity squared. Thus we see that the posterior for mu, given y, follows a normal distribution with mean y bar and variance sigma squared over n. This should look just like the maximum likelihood estimate. In the case that sigma squared is unknown, the standard non-informative prior is f of sigma squared is proportional to 1 over sigma squared. This is equivalent to an inverse gamma with both parameters equal to 0. This is an improper prior, and it's uniform on the log scale of sigma squared. In this case, we'll end up with a posterior for sigma squared, which is an inverse gamma with parameters n minus 1 over 2 and 1/2 the sum of y sub I minus y bar squared. This should also look reminiscent of quantities we get as a frequentist. For example, the sample standard deviation. Choosing a uniform prior depends upon the particular parameterization. For example, thinking about the normal distribution, suppose I use a prior which is uniform on the log scale for sigma squared. So f of sigma squared is proportional to 1 over sigma squared. Suppose somebody else decides they just want to put a uniform prior on sigma squared itself. F of sigma squared is proportional to 1. These are both uniform on certain scales or certain parameterizations, but they are different priors. And so when we compute the posteriors, we will get different posteriors. The key thing is that uniform priors are not invariant with respect to transformation. Depending upon how you parameterize the problem, you can get different answers by using a uniform prior. One attempt around this is the Jeffreys prior. Jeffreys prior is defined as the prior proportional to the square root of the Fisher information. In most cases, this will be an improper prior. For the example of normal data, the Jeffreys prior is exactly the prior we've seen before. It's uniform for mu, and then for sigma squared, it's uniform on the log scale. This prior will then be invariant transformation. We'll be putting the same information into the prior, even if we use a different parameterization for the normal.
in the example of a Bernoulli or binomial, the Jeffreys prior turns out to be theta to the minus 1/2, 1 minus theta to the minus 1/2, which is a beta distribution with parameters 1/2 and 1/2. This is a rare example where the Jeffreys prior turns out to be a proper prior. You'll note that this prior actually does have some information in it. It's equivalent to an effective sample size of 1 data point. However, this information will then be the same not depending upon the parameterization we use. In this case, we have theta as a probability, but another alternative used in probabilities calculations, sometimes we model things on a logistic scale. And in that case, we can transform everything, and using the Jeffreys prior, we'll maintain the exact same information. Other possible approaches to objective Bayesian inference include priors such as reference priors and maximum entropy priors. Finally, I'd like to mention a related concept, which is empirical Bayesian analysis. The idea in empirical Bayes is that you use the data to help inform your prior, such as using the mean of the data to set the mean of the prior distribution. This approach often leads to reasonable point estimates in your posterior. However, it's sort of cheating because you're using the data twice, and as a result, it may lead to improper uncertainty estimates. This demonstration is on fitting linear regressions in R. We'll look at 2 examples, one simple linear regression with just one explanatory variable, and one case of multiple regression. We'll do this using data sets that are freely available online. The first one is looking at space shuttle damage. So this is thinking back to the time that the Challenger shuttle was launched and we had the Challenger disaster. There were 23 previous launches before Challenger disaster. What we'll look at is the temperature at the time of launch in degrees Fahrenheit and an index of O-ring damage. This is labeled I in this data set. Let's go take a look at a data set. So this is hosted at the University of Alabama, Huntsville. Here's the data set. 23 previous launches, the temperature in degrees Fahrenheit, and the index of O-ring damage. You can see most flights had no damage, but some had 2, 4, or 11 units of damage. In R, we can read in a data set directly from a URL online using the read.table command. So I'll do that here, store it in an object called O-ring, and this one does have labels, and so we'll specify header equals true. Just a note here that after I tell it to paste, I have to hit the return key to get R to execute that. All right, we've read in this data set. If I want to be able to use the labels, I use the attach command to be able to access the labels. R gives me a warning because one of the labels is T. Here T is for temperature, but built into R, capital T also stands for true. So while we're using these labels, we won't be able to use capital T as a shortcut for true, but we're not going to be using that today anyway. So just to verify, we can look at, here's our data set. We read in all 23 rows. We've got temperature and damage. We can make a quick plot of this, visualize the data. Here we can see the 23 previous launches. All of the launches that had no damage were on warmer days. All of the launches on colder days had some type of damage. So there does look like there's some effect of temperature on the state of the O-rings. Let's fit a linear regression to predict damage based on temperature. I'm going to use the LM command in R. LM stands for linear model. It's a linear model of damage modeled on temperature. So here temperature is the independent or explanatory variable, and damage is the dependent variable. Now I've stored it in this object. If we want to see the results, we can use the summary command. And here's a summary of the results. There's a fair amount of information. What's most important here is here's the coefficient for the intercept, here's the coefficient for the slope. These are the standard deviations for the marginal distributions for the intercept and the slope. If we were a frequentist and we want to do a frequentist significance test, these are the t-values and the p-values associated with the t-tests. The standard error for the regression is 2.1. If we're interested, the r-square is 0.4. We can add a fitted line to the scatter plot. In R, the lines command will connect the dots and create a line. We can plot the temperatures and the fitted temperatures, and we get them out of the linear model object by using the fitted function on the linear model object. Here we can see the fitted line, and that as temperature increases, the damage goes down, or as temperature decreases, the damage goes up. This is just an approximation. It's not going to go through all the points because there's a lot of noise in the data, as is typical with real-world data. Our slope estimate is minus 0.24. So roughly, for every 4 degrees the temperature gets colder, we see a 1 unit increase in damage. We could look at a 95 posterior probability interval for the slope. Here I'm taking the fitted value for the slope, and the marginal distribution, posterior distribution, is a t-distribution with 21 degrees of freedom, and it has the scaling factor of the standard error of the coefficient, 0.06349. So plugging that in, I get a 95% posterior probability interval that goes from minus 0.375 to minus 0.111. This interval does not include 0, so we can be pretty sure that there is a negative relationship between temperature and damage. Note that these intervals are the same as the frequentist confidence intervals when we're using the standard reference prior for a Bayesian analysis. The day that Challenger was launched, the temperature was actually 31 degrees Fahrenheit. How much O-ring damage would we predict? So we're looking at the y-hat value for an x of 31, or in this case a t of 31. We can compute this by hand by pulling off appropriate elements, the intercept and the slope. So the intercept plus the slope minus 0.24 times the value 31, and we get a predicted value of 10.82. We can see that's a fairly large amount of damage that we predicted. That makes sense because 31 is actually off the edge of this chart. The lowest value we observed was 53. 31 would be farther to the left, and we'd expect to see a fair amount of damage. We can also use the coefficient command in R to get coefficients out of a linear regression model object. In this case, it will give us a vector of all the coefficients. Here, the 18.36 and the minus 0.24, the intercept, and the slope. So we could use this to compute a fitted value, taking the intercept as the first value of the vector of coefficients, and the slope as the second value of the vector of coefficients. And you see here we get essentially the same answer. There's maybe a little bit of rounding error when I just pull the numbers off by hand. We can also think about a prediction interval, a posterior prediction interval. So if we're going to launch at 31 degrees, what's a 95% predictive interval for what we might see in damage? This is going to be a larger interval than just a fitted interval. we can use the predict command in R. It will give us also this predicted value, but it will give us a predicted interval. Predict command starts by taking the linear model object. We then have to tell it where we want to predict. We give it a data frame of the values of the independent variables, in this case a temperature of 31, and then we tell it we want a prediction interval. So here, again, we verified that the fitted value is 10.82, but a 95% predictive interval goes from about 4.05 to 17.59. We could also verify this by hand using a formula that's in the materials posted online for this lesson, and see that we get a lower bound of, again, about 4.05. So a little bit of rounding happening here. And the upper bound would be comparable, changing this minus to a plus. These predictive intervals are the same intervals that we get if we were a frequentist. So using the Bayesian reference prior allows us to use all the standard regression tools. One thing we can do different as a Bayesian is we can ask, what's the posterior probability that the damage is greater than 0 if we launch at 31 degrees? So here we're going to use the same predictive distribution, but use it to make a probability statement. So we can ask, what's the probability that damage will be greater than 0? So it's a t distribution. I'm going to ask, what's the probability of t with this center and this scale is bigger than 0? The pt command will give us the probability it's less than 0, and so we take 1 minus that to get the probability it's bigger than 0. Probability that the damage will be bigger than 0 is 0.998, very close to 1, so it's extremely likely that there will be damage if we are to launch at 31 degrees Fahrenheit. Now let's take a look at a multiple regression example. This example is one of the classic data sets. Galton, in the 19th century in Britain, was looking at predicting the heights of children from the heights of the parents. All these measurements are in inches. Let's take a quick look at the data set. Here we can see that there's a number of different families. In each family, they looked at all the kids in the family. They looked at the height of the father in inches, the height of the mother in inches, the gender of the child, the height of the child in inches, and how many kids are in that family. So let's read this into R. This one seems to trigger a warning message in R. R sometimes gives warning messages of things happening behind the scenes, but this won't affect any of our analyses. So let's use the headers. The labels for the variables are family, father, mother, gender, height, and kids. Let's take a quick look graphically at the data. Focusing on height as the variable we're trying to predict, we can look at this column here and see that boys in general are a little bit taller than girls. The tallest children tend to have taller parents. The shortest children tend to have shorter parents. It's not clear that there's any relationship between the number of kids in the family and the height. Let's look at regression for all these variables in predicting the height of the children. We can see that there's a clear effect for the height of the father, clear effect for the height of the mother, clear effect for the gender of the child, but that there's not such a clear effect for the number of kids in the family. The standard error is close to the size of the estimate, and so this distribution is very close to 0 and includes 0, and so we may not want to use this variable as it may not be that helpful in actually predicting, and including too many variables will increase your predictive variance. So let's take a look at what happens if we take that variable out. Here we can see that all these variables now have strong effects. There's not much change in fit. If we look at our R-square, it's roughly 0.64 and roughly 0.64. And so this is a better model for us to use. So we'll stick with this regression model where we're predicting height as a function, height of the child as a function of height of the father, height of the mother, and gender of the child. We can see that each extra inch taller a father is correlated with about a 0.4 inch increase in the height of the child. Each extra inch taller a mother is a little more than 3/10 of an inch taller in the child. And that on average, boys are about 5.2 inches taller than girls. We could ask, what's a 95% probability interval for the difference in heights between boys and girls? The marginal distribution for the slope parameter for gender is going to be a t-distribution with 894 degrees of freedom. And so we can use that to get a 95% probability interval for this slope effect of gender and see that that ranges from 4.94 to 5.51. So indeed, boys are going to be a little more than 5 inches taller than girls on average. We can also look at prediction intervals. Again, a reference Bayesian analysis will give us the same intervals as a frequentist. So we could ask, what's a predicted height and predicted 95% probability interval for a child's height when the father is 68 inches tall, the mother is 64 inches tall, and the child is either male or female? We can see that the predicted height for a male child is 68.75 inches, with a probability interval ranging from 64.5 to about 73. If it's a girl, then the predicted height is 63.5, with a prediction interval ranging from 59.3 to 67.76. This demonstration is on using Microsoft Excel 2016 with the Data Analysis Toolkit for doing linear regression. We'll take a look at two examples, one of simple linear regression with just one explanatory variable, and one example with multiple regression. The first example is looking at space shuttle launches and damage to the O-rings. This is the context of the Challenger disaster. There were 23 previous launches before the Challenger disaster. Let's take a look at that data. This is a publicly available data set that's available at the University of Alabama, Huntsville at this web address. Here we can see the 23 previous launches, the temperature in degrees Fahrenheit, and an index of damage to the O-rings. Most launches had no damage, but some of them had 2, 4, or 11 units of damage. We'll copy all of this data and paste it into Excel. Let's take a look at a plot of the data. We can do this: insert, chart, XY scatter plot. Make the chart a little bit bigger so we can see it better. We can see that all of the flights that had no damage were on warmer days. All the flights on colder days had some amount of damage. We can add chart element trend line, linear, put a linear regression line onto this chart. So here's the fitted line, and we can see that as it gets colder, we expect to see more damage. We can quantify that using a linear regression model. So we'll go to Data, Data Analysis, Regression. Our y variable, the response, or dependent variable, will be the index of O-ring damage, and that goes from I2 to B2 to B24. The explanatory variable, the x variable, is the temperature, and that goes from A2 to A24. We'll put the output into the same spreadsheet so that we can use the results. Here Excel has computed linear regression for us. An R-square of 0.64, standard error of 2.1, there's 21 degrees of freedom. The fitted intercept is 18.365, and the fitted slope is minus 0.24. The slope gives the relationship between temperature and predicted damage. It's saying approximately for every 4-degree decrease in temperature, we expect to see a 1-unit increase in damage. That makes sense with this negative slope. Excel also gives us a 95% interval for the slope. Under the Bayesian analysis, this is a posterior interval. Using a reference Bayesian analysis, we get the exact same interval as we would for a frequentist. We can see how this is computed by hand. For example, the lower portion of the interval, minus 0.375. That's going to be the fitted value minus the standard error times the value from a t distribution, a t with probability 0.975, and degrees of freedom as given by the regression. Thus, we can replicate by hand what Excel has given us in the table. Suppose we want to predict how much damage we expect to see if we launch at 31 degrees. That's pretty far below the actual data that we've seen so far, and we're going to expect to see a fair amount of damage. Predicted value, y hat, is going to be the intercept plus the slope times the x value we're predicting at, in this case 31. We get a predicted value of 10.82. So at 31 degrees Fahrenheit, we expect to see, on average, almost 11 units of damage, which is about as high as we've seen in the data set. We can ask, what's a predictive interval for this launch at 31 degrees? So thinking about a posterior predictive interval. These, under a reference Bayesian analysis, will be the same, again, as the frequentist predictive intervals. And so this is thinking about a new observation when we launch at 31 degrees. I'm going to copy and paste in a formula. This formula is in the materials associated with this lecture online. This will give us the lower end of the interval, and then using a plus instead of a minus will give us the upper end of the interval. Thus, we get an interval that runs from about 4.05 to 17.59. This will be a 95% predictive interval for all future launches at 31 degrees. You can see that 0 is not included in this interval, so we're pretty confident that we'll expect to see O-ring damage if we launch at 31 degrees. So far, we've gotten pretty much the same answers if we're using a Bayesian analysis or frequentist analysis. A question we can ask as a Bayesian that's difficult to answer as a frequentist would be, what's the posterior probability that the damage index is greater than 0 for a launch at 31 degrees Fahrenheit? Here we'll use the marginal predictive distribution, posterior predictive distribution, and that's a t-distribution. T-distribution with center 10.82 and scaling factor 2.1. The t-dist function will give us the probability of it being less, and so if we want the probability it's greater than 0, we'll take 1 minus that value. Plugging this in, Excel gives us a probability of 0.998. Thus, we have extremely high probability of seeing O-ring damage if we launch at 31 degrees Fahrenheit. Now let's move on to a second example. This example is a classic data set on predicting the heights of children from the heights of the parents. This was done by Galton in 19th century Britain. All these height measurements are in inches. Let's take a look at the data set. So he measured heights of children in a number of different families, measured the height of the father in inches, the height of the mother in inches, the gender of the child, male or female, the height of the child in inches, and how many children were in that family. So we'll copy this into a new Excel spreadsheet. In order to fit a regression in Excel, a multiple regression, it wants us to have all of the explanatory variables, all the independent variables, together in one block. Because height is somewhere in the middle, we'll make a new block over here with all the explanatory variables. So kids is a potential explanatory variable, height of father, height of mother, and gender of child. I'm going to start by copying father and mother and put them over here in columns G and H. So now I've got kids, father, and mother together. Gender, Excel is going to want me to have numbers, not labels of male and female. So I'm going to create a new variable called genderM. This will take a value 1 if the child is male and a value 0 if the child is female. So in particular, we can use the if function in Excel. And so I can say if the value in column D is equal to male, then I want the value 1, and otherwise I want the value 0. With this formula now, I'll cut and paste it into all the rest of the column. This is a fairly large data set, and so we'll see it goes down to row 899. So now I've created a contiguous block of my explanatory variables, and I can use this to make a regression. My y range is going to be height. It's going to be going from E2 to E899. My x range is going to be kids, number of kids in the family, the height of the father, the height of the mother, and the gender. And this is going to go from F2 to I899. The output range will need to move over compared to where it was last time. And so here Excel gives us a response. R squared of 0.64, 893 degrees of freedom, and some coefficients here. Variable 1 is the kids, variable 2 is the height of the father, variable 3 is the height of the mother, and variable 4 is the gender. We can see that for parents' heights and for gender, these are highly significant and important variables. The coefficient is much larger than the standard error. On the other hand, for the size of the family, the coefficient is not much larger than the standard error. So this is a slope that's very close to 0. And we might say for a frequentist that it's not statistically significant. In general, we don't want to include extra variables that are not helpful with prediction because they tend to increase the predictive error. So let's fit this again, but without the number of kids in the family. Here I'll change the x input range to start in column G. And we'll overwrite. Now we can see our R-square is almost the same, still about 0.64, but that all of our coefficients are important for the model. All the values are much larger than their standard errors in absolute value. We can see that on average, each extra inch of height of a father results in about 4/10 of an inch of height in the child. Each extra inch of height in the mother results in a little over 3/10 of an inch of height for the child. And that on average, boys are 5.2 inches taller than girls. Excel gives us a 95% posterior interval for this difference in height by gender. It goes from 4.94 to 5.51. This would be a 95% posterior probability interval if we're doing a Bayesian reference analysis, but it is also the same as the frequentist confidence interval. This segment will demonstrate linear regression using Excel plus Stat Plus, the free extra software. This is for versions of Excel where the data analysis toolkit is not available. We'll look at two examples of linear regression. The first is a simple linear regression where we only have one explanatory variable, and the second is a multiple regression. This first one is looking at space shuttle data, and so this is going back to the Challenger disaster. This is freely available data currently hosted at the University of Alabama, Huntsville. What this data shows is before the Challenger fatal flight, there were 23 other flights. It has the temperature in degrees Fahrenheit and an index of the amount of O-ring damage for that flight. You can see that with most flights, there was no damage, but in some flights there were 2, 4, or 11 units of O-ring damage. You can also see that the damage tends to be bigger for colder temperatures, and that there tends to be less damage at warmer temperatures. We'll highlight all of the data and copy it here into Stat Plus. Stat Plus will allow us to do a regression. We want to predict the damage index, so that's our dependent variable, or our response variable, and predicting it from the temperature, that's our independent variable, or explanatory variable. Stat Plus gives us a new sheet with all the linear regression results. We can see we have an R-square of 0.41, a standard error of regression of 2.1, there's 21 degrees of freedom, the estimated intercept is 18.365, the estimated slope is minus 0.243. This estimated slope says that approximately for every 4 degrees colder at launch, we expect to see 1 additional unit of damage to the O-rings. We can look at what's a 95% posterior probability for the slope. Stat Plus gives us this actual interval. The interval goes from minus 0.375 to minus 0.111. We could also compute this by hand. Let's just look at the lower limit of this 95% interval. we could see this as the fitted value minus the standard error times the value from a t-distribution with probability 0.975 and degrees of freedom, the degrees of freedom from the regression, in this case 21. Here we can see that doing this by hand gets us the same answer as in the table. This is a 95% posterior probability interval using a reference Bayesian analysis, or reference prior. This turns out to be the same interval as we get as a frequentist, creating a 95% confidence interval. But using a reference Bayesian analysis, we can give this a full probability interpretation, saying that we have a 95 posterior probability that the true value of the slope will be in this interval. Suppose we want to predict the actual temperature at launch for Challenger that day was 31 degrees Fahrenheit. That's much colder than the coldest flight previously. We'd like to predict how much damage do we expect to see at 31 degrees Fahrenheit. So this predicted value is going to be the fitted intercept plus the fitted slope times this input value, in this case 31 degrees. We can see then that the predicted amount of damage is 10.82 units. This is relatively large, about as big as anything else we've seen in the data set. We can ask, what's a 95% posterior predictive interval? So we're thinking about the posterior predictive distribution, looking at a new observation. I want to ask, what's an interval such that there's 95% posterior probability that the new observation will fall in that interval? This will be a t-distribution that's centered at our prediction of 10.82. And we'll have a scale based on the standard error of regression and the rest of the formula that's available in the notes online associated with this lesson. This formula uses partly the distance from this new point to the rest of the data. So our new value of 31 relative to the other data. So we're going to go back to the first sheet where we have the rest of this data, and so we can access that. Here's the lower interval, and here's the upper end of the interval. So we can see that a 95% posterior predictive interval runs from about 4.05 to 17.59. Thus we say we have a 95% posterior predictive probability of getting an observation between 4.05 and 17.59 units of O-ring damage. It seems pretty likely that there will be a significant amount of damage to the O-rings if we were to launch at 31 degrees Fahrenheit. Note that again, under a reference Bayesian analysis, this is the same interval as we get as being a frequentist and asking what's a predictive frequentist interval. One thing we can do differently as a Bayesian that's difficult to do as a frequentist is we can ask about posterior probabilities. For example, we can ask what's the posterior probability that the damage index will be greater than 0 for a new observation of a launch at 31 degrees Fahrenheit. So again, we're going to use the posterior predictive distribution, which is a t-distribution. It's a t-distribution with center 10.82 and this somewhat complicated scale factor. So we paste this formula in, and in this case, some versions of stat plus might work, and other versions this may throw an error code. Apparently with some versions of stat plus, it gets cranky if we have a negative number going into this t-distribution function. T-distribution is symmetric, and it should work for a negative number, but in this case it doesn't seem to be working. So instead of taking 1 minus the cumulative at the negative value, we'll look at the value up to 10.82 in this case because it's a symmetric distribution. So we'll just flip this around. We'll get the same answer in this case. So here we can see the posterior probability of getting a damage index greater than 0 at 31 degrees Fahrenheit is 0.998. Probability is almost 1 that we'll have damage if we launch at 31 degrees Fahrenheit. All right, let's move on to a second example of regression. This one is a classic data set back to the 19th century where Galton was trying to predict the heights of children from the heights of the parents. Here we have data from a bunch of different families. Some families have more kids than others. This first family had 4 kids. This family had 4. This family had 2. We can see for each child, we have the height of the father in inches, the height of the mother in inches, the gender of the child, and the eventual height of the child in inches, as well as the number of kids in the family. So we want to be predicting the height of the children from the heights of the parents, and potentially also the gender and the number of kids in the family. We're going to need to do a little manipulation to this data set before we can stick into the regression. So I'm going to do that first in Excel. In particular, the issue is that gender is coded as M and F for male and female. But in terms of running a regression, we're going to need numerical values. So I'm going to create a new variable called gender M, and I'm going to make this have the code of 1 if the gender is M, and a code of 0 if the gender is F. So I pasted in this formula using the if command in Excel. And now I can copy and paste this into the rest of the data set. Turns out there are 899 rows in this file, so we'll go down, we'll paste this in to the rest. But the key is we need to translate the M's and the F's into 1s and 0s so that then Excel or Stat Plus can do the regression, because they're both expecting numerical values and they can't deal with the categorical variables of M and F. Okay, so now I have 0s and 1s. And I'm going to do my regression again in Stat Plus. So I will open up a new sheet. In Stat Plus, I can paste in this data set. I can now do a regression. I want to predict the height of the children based on the father's height, the mother's height, my numerically coded gender variable, and the number of kids in the family. So here we've run our multiple regression. We get an R-square of 0.64, standard error regression of 2.15, 893 degrees of freedom, and here are our coefficients. An intercept of 16.18, slope coefficients for each of the explanatory variables, the standard errors for each of those slopes. You can see that for most of them, the coefficient is much larger than the standard error. But in the case of the size of the family, the number of kids in the family, the coefficient is not much larger than the standard error. In fact, if we were frequentist, we might do a t-test and say, is this variable significant? In this case, we'd fail to reject it, say this variable is not particularly significant. As a Bayesian, we might just look at the coefficient relative to the standard error and see that its posterior interval includes 0. We generally try not to include variables that are not adding much to the regression because they don't help with prediction and they actually increase the variability of our prediction. So in this case, I'm going to go back and I'm going to fit the regression again without using the number of kids in the family. So predicting the height of the children based on the height of the father, the height of the mother, and the numerically coded gender variable. So now I get basically the same R-square of 0.64, same standard error regression, 2.15. We have one more degree of freedom because we have one fewer explanatory variables. Now, the intercept and all the slope coefficients are all much larger than their standard errors. We can see that the fitted slope for the father's height is 0.4. This says that for every extra inch taller a father is, that is correlated with another 0.4 inches of height in the child. Each extra inch of height in a mother is correlated with a little more than 0.3 of an inch of height in the child. And that on average, boys grow up to be 5.2 inches taller than girls do. The table gives us a 95% posterior probability interval for the difference in heights by gender. We can see that this interval goes from 4.94 to 5.51. So we can say there's a 95% posterior probability that the difference in height by gender is in this interval under a standard reference Bayesian analysis. This is also then going to be the same interval we'd get under a frequentist confidence interval.
This is the conclusion of this course. As you've seen, both frequentist and Bayesian approaches offer coherent methods for understanding of uncertainty and for data analysis. I hope that I've convinced you that the Bayesian approach better matches our intuition of uncertainty and provides answers that are more easily interpreted. No approach to statistics is completely objective. The Bayesian approach makes our assumptions more explicit. Both Bayesian and frequentist approaches are valuable for a whole range of data analysis as well as scientific discovery. The Bayesian approach provides better quantification of uncertainty. If you do want to go farther with Bayesian statistics, the next topics to explore would be hierarchical modeling and the fitting of non-conjugate models with Markov chain Monte Carlo, or MCMC. I hope you've enjoyed this course and that you've gained an understanding of the Bayesian approach to statistics, and I hope that you find it useful in what you do.